systems, or perhaps you are interested in car radar to enable autonomous driving, or you want to create your own startup company in the domain of wireless. And in these situations, you need to have a solid background in microwave engineering and antennas. And we as a team, the three of us, we provide you more than 50 years of experience that we're going to share with you in the course. And this course is really unique because it's online, but it also provides you with a solid understanding of both microwave engineering and antennas, including active devices.
Here you see a typical example of a phased array system for 5G. It's consisting out of many antennas operating in the 28 GHz range. And on the back side of this panel we will find the front-end ICs, the active devices which drives these antennas. And we will explain in this course of microwave engineering how you can make this.
So as you can see, in order to make 5G possible, you need to integrate the electronics and the antennas into one single module. A trend that we see now for the future is that the antenna integration or the antenna and electronic co-integration will become an even more important topic. As you can see here, for example, the antenna might be integrated onto the chip itself. In order to achieve this, you need a solid background in electronics as well as the antennas.
This online course, Microwave Engineering and Antennas, will become available on the Coursera platform as of November 2020. And it will include several elements. Of course, we will talk about theory, we will explain it in web lectures. There's an open source book available, we have several quizzes, and we will include hands-on workshops and challenge-based design assignments. And we are looking forward to see you back again in the course. Welcome to the general introduction of the Microwave Engineering and Antennas course. My name is Bart Smolders and I'm a professor in the Department of Electrical Engineering at Eindhoven University of Technology in the Netherlands. And I'm also associated with the Center for Wireless Technology Eindhoven. Now this course is a master level course that could fit within an electrical engineering program. And in our program in Eindhoven, this course is a master course. And this course is tuned towards the trend that we see in, for example, 5G and 6G wireless communication systems, that electronics, microwave electronics, is integrated with antennas, becoming more complex systems. And for that reason, it's necessary to provide students and other engineers with the background both in microwave engineering but also in antennas. And this course provides you an ideal combination of both disciplines. Therefore, the objective of this course is first to provide you an introduction into microwave engineering, and we will focus on both on passive and active components. Then we will provide you with an introduction into antenna theory, including phased arrays. And the course will also include several hands-on design challenges where you will learn to use state-of-the-art design tools to design microwave circuits and antennas. Now the general structure of the course is that we have 4 modules. So the first module is mandatory, so it's an introduction that includes an application overview, some trends, but also some practical things like how to use the quizzes that we will provide, the online quizzes. Then we will start with the first real module on passive microwave circuits. We will continue with antenna theory and we will conclude with active microwave circuits. In principle, if you want to finish the course with an exam, then you need to follow all 4 modules. But if you want, of course, then you could decide to only follow 2 or 3 modules. Now, what do we require from you? First of all, we require you to have some background in circuits, so electronic circuits, like being able to apply Ohm's law on resistor, capacitor and inductor networks. And we would like to have some bachelor level or equivalent level there. Next to that, some background in electromagnetics, so both static and dynamic fields would be appreciated, also on bachelor level or equivalent, of course. Now, the team of lecturers, besides myself, we have Professor Domien Leenaerts. He's a part-time professor at our university and is also a fellow at NXP Semiconductors, and is really an expert in the design of active microwave circuits. Then we have Ulf Johansson, and he will be responsible for the hands-on activities in this course. And myself, I will focus on the passive microwave circuits and antennas. Now, besides web lectures, we also have a lot of online quizzes where you can practice the theory, and we have all kind of additional exercises as well. Next to that, we have labs where we are going to teach you how to use state-of-the-art simulation tools. Now, some additional study material that we will provide you. First of all, we have a book which is available online for free. The book Modern Antennas and Microwave Circuits really covers all the material that is part of this course as well. And of course, we will provide you with some additional material when needed. Now, what do we expect from you besides the background knowledge? We expect from you that you watch the web lectures each week. We expect from you that you perform the quizzes and the lab exercises. And we also would like you to be part of the discussion forum where you can seek help, first with your peers, but of course we will also be available to provide answers to your questions. Now, some other practical requirements. You need, of course, to have access to a personal computer or a laptop, and you need to be able to download some open source software that we're going to use for design of microwave circuits and antennas. Having said that, I wish you a lot of success in the course, and I hope to see you back during the first real web lecture. Welcome to this second web lecture in the course of Microwave Engineering and Antennas. Today we're going to talk about applications. So the objective of this particular lecture is to describe the trends that we see in wireless applications, and I'm also going to introduce a couple of very interesting examples. The first trend that we see is an increase in operational frequency. So if we plot the new systems, wireless systems that have been introduced in the past 100 years, and we plot it versus frequency, then we see on a logarithmic scale, we see a straight line, which means that the operational frequency of new services tends to increase. And that has the benefit that we have more bandwidth available. And of course, we also require to use higher frequencies because simply the lower frequencies are already occupied by existing applications. The second trend is that the bandwidth and the associated data rate is also increasing, and that's visualized by this graph, which is, was presented by Edholm in a publication in IEEE Spectrum already in 2004. And he found out that the bandwidth of new systems, wireless systems, seems to double each 18 months. It's comparable to Moore's law in electronics. And this trend is also visible if you look at the evolution of all the wireless standards. Well, you're all familiar with 4G, with 3G, and of course 5G is coming soon. If you consider the data rate that is offered by all these systems, going, for example, from 4G to 5G, we expect an increase in data rate of, let's say, from 4G 100 megabits per second to, in 5G, 10 gigabits per second. If you then come back to Edholm's law, a doubling of the bandwidth or data rate in 18 months, then indeed we see if we go from 4G to 5G, which is, let's say, a time span of 10 years, we exactly meet this Ohm's law. So we exactly are on par with doubling of the data rate in 1.5 years. And of course, the next step is to go to 6G. So applications in wireless communications, of course, antennas and microwave engineering is very important for the design of base stations, which are used for 4G, 5G, and the following generations in the future. A base station provides a connection to mobile users, and a base station in 5G will be able to electronically perform beam steering. And a nice example of that is work that we are doing at Eindhoven University of Technology in cooperation with NXP, where we have developed a prototype, a phased array in this case, that can be used in future for 5G new radio base stations, which will operate at much higher frequencies as being used now for 4G. It will operate around 30 gigahertz. And here you see an example of a phased array which includes electronics on the backside. So this is a 8x8 phased array with two polarizations. The backside of this phased array consists of many chips, integrated circuits. In this case, they are made with silicon technology, and they provide all the phase shifting and amplitude manipulation that is required to perform beam scanning of the phased array. Of course, base stations, next to base stations in wireless communication, we have the users, and of course the mobile phone, the smartphone is the most used mobile application. In a smartphone, if you would open it up, then you see many examples of wireless systems, wireless applications, ranging from Wi-Fi, Bluetooth, 4G, 5G, GPS, NFC, etc., etc. And all these systems require electronics, require antennas, interconnect, etc., etc. So for the design of these systems in mobile phones, the concepts that we're going to discuss in this course are really crucial. Next to wireless communication, what we know, let's say on land, 4G, 5G, there's also satellite communication, which is also emerging. Typically it works between 10 and 40 gigahertz. Here you see an example of a satellite terminal receiver unit. It includes a lot of components, as you can see, a lot of, let's say, funny circuits, which you might not recognize yet. There's also an antenna input, which is connected to a horn antenna, which feeds a reflector. The circuits that you see here on this PCB, some of these circuits we're going to discuss in more detail in this course. Traditionally, application of microwave engineering antenna is of course radar. A lot of concepts originate from the development of radar, already starting in the Second World War. A phased array radar, as shown here, operating at L-band, is a nice example of modern radar systems. In this case, this is an L-band array with 1024 antenna elements, and each antenna element is connected to electronics, and the electronics provide phase shifting, amplitude manipulation to have electronic beam steering. Another domain of applications, which is a nice spin-off of all the developments that we do at wireless communication and at radar, is in the medical area. An example shown here is hyperthermia. In fact, you have a phased array of antennas operating at frequencies which are relatively low. So in this example, it's 433 megahertz. The array elements are fed by power amplifiers, and by combining all these signals, it's possible to heat up a particular part of the body. And this treatment, hyperthermia treatment, is used to heat up tissue, tumor tissue, to a temperature of about 43 degrees. And by doing that, other therapies like chemotherapies are more effective. Another application domain involves scientific instrumentation. And a nice example, of course, is radio astronomy, where a lot of facilities are already available operating at low frequencies like 10 megahertz up to 500 gigahertz. A nice example of a system which is currently being built in South Africa and in Australia is the square kilometer array. And an artist's impression of this system is provided here. It consists also of phased array technology that provides multiple beams towards the sky, so providing for the radio astronomers a wide field of view. It also provides extreme large bandwidth, frequency bandwidth, and of course radio astronomers only receive, so you don't transmit energy. To summarize this web lecture, I have discussed two trends which are can be observed in a lot of wireless communication systems and other applications. So the first trend is that we move to higher frequencies, coming from RF frequencies to microwave frequencies to millimeter wave frequencies, and in the future to terahertz frequencies. We also see a trend towards more bandwidth. I introduced Atom's law. In application domain, I have shown a couple of examples. Of course, wireless communications, radar, medical domain, and radio astronomy. Thanks for watching this second video and hope to see you back soon. Welcome. In this web lecture, we're going to talk about time harmonic signals and fields. In fact, in the entire course, we will assume that all these signals and fields are time harmonic. And you might be familiar already with time harmonic signals, for example, from a bachelor course that you took on circuits. Anyway, in this web lecture, we will give a short summary of time harmonic signals and fields. In particular, we're going to talk about the representation of signals in the time domain. We will do the same for signals in the frequency domain, or what we also call phasors. Then we will have a look at the time average power, and finally we will discuss time harmonic fields. Now, a time harmonic signal, for example a voltage, could be written in the following way. So plotting this voltage versus time would result in this kind of figure. So we see clearly the cosine omega t plus phi dependence. We have an amplitude, in this case it's V naught, and we have a radial frequency, omega, which is equal to 2 pi f, and f is the frequency in hertz, and it's related to the time period as indicated here in the figure. This time domain representation can also be expressed in the following way as the real part of some complex representation of the voltage. And this complex representation can also be written as a complex voltage, V times e to the power j omega t. And V is then known as the time-independent complex voltage, which is a phasor. And actually, V is the frequency domain representation of the voltage. Usage and properties of this frequency domain voltage in this case, or other signals. First of all, we will always omit the term e to the power j omega t when we work with phasors, so when we work in the frequency domain. On top of that, one of the important properties that we will use several times in the course is that if in the time domain we have a time derivative, for example in Maxwell's equations or in transmission line equations, a derivative to time simply transforms in the complex domain, in the frequency domain, to a simple multiplication with the term j omega, and that simplifies a lot of mathematics. Since we work with time harmonic signals, it's relevant to look at the power, since this often gives a lot of confusion with our students. Let us consider a very simple circuit like shown here. So we have a load connected to a source with a certain voltage, V, and through the load we have a current, I. Now the voltage in the time domain and the current in the time domain can be represented as indicated in the phasor notation, so the real part of a complex voltage and a complex current. And the complex voltage and current in the frequency domain are given as indicated here, where phi1 and phi2 are, for this moment, unknown phases. Now, looking at power, the dissipated power in the load, we could talk about an instantaneous power, which is the product of the voltage and the current in the time domain. However, if we use time harmonic signals, then it's more appropriate and common to talk about the time average power, so averaged over one period of time. Which means that we have to integrate the instantaneous power over one period and then divide by t, by the time period. Then we get the average power. If we substitute the expressions for the voltage and the currents and do the integration, so we have to integrate this function here, we can show that finally the time average power can be written in this form. So it's the real part of the complex power, and the complex power is the product of the complex voltage times the conjugate of the complex current. And since we average over one period, a factor half appears, and this is very important. It's also often neglected by students who only consider the complex power. So take a note of this, and we will use this time average power quite often in this course. Now, apart from signals, which are scalars like voltage and current and power, we can also talk about time harmonic fields. And the fields, electromagnetic fields, are vectors. So for example, if we would write the electric field, the time domain representation of the electric field vector of, for example, a plane wave in free space that propagates, it would look like this. So it's a certain amplitude with a direction, E naught, times cosine omega t minus k naught r plus phi. R in this case is a position vector, so indicates where we are, and k naught is the wave number, which is equal to 2 pi over lambda, over the wavelength. The distance away from the origin of the coordinate system is then r, is the amplitude, the absolute value of the position vector. Now, this representation of a plane wave might be familiar to you. We can then also write this time domain representation in terms of the real part of a complex representation, as indicated here. So we have the vector E, which is a phasor, so it's the frequency domain representation of the electric field in this case, times e to the power j omega t. And this vector E is time independent and is also called a phasor, and can be written in this form. So it's the amplitude vector E naught times e to the power j phi times e to the power minus j k naught r. And this representation we will use throughout this course as well. Now, to summarize, in the entire course we will assume time harmonic signals and fields. In addition, we have introduced time domain and frequency domain representations of signals. We also looked at vector quantities next to scalar quantities, and we talked about the time average power. Thanks for watching, and hope to see you back next time. Welcome again at this third web lecture of the Microwave Engineering and Antenna course. Today we're going to talk about transmission lines, and in particular we're going to talk about the lossless line. The objectives of this particular course are to introduce you the theory of ideal transmission lines, to apply this theory to a terminated lossless line, and to discuss a few examples. Well, in the last web lecture we talked about applications. One of the applications is a base station used for wireless communications, for 4G, 5G and in future for 6G. And what you see is that modern base stations apply the concept of beam steering, electronic beam steering with phased arrays. Now, such a phased array beam steering could look like this. It's a system that we developed in my group with students. It's a board where you recognize on this side in the red box, you recognize 4 antenna elements which are printed on a PCB. In this case they represent dipole-like antennas. You also recognize a circuit which is a power splitter, so it has 1 input and 2 outputs. And you recognize a circuit which creates a time delay between the various channels, and it uses a MEMS switch to switch between a shorter and a longer line. Now, this PCB shows many examples of transmission line circuits, components that we're going to discuss throughout this course. Now, examples of transmission lines, there are many examples. The most common transmission line that you all know about is the coaxial cable. A parallel transmission line with 2 parallel wires, also called twin lead, is something which has been used in the past as well. More modern versions of transmission line are all embedded in planar technologies like PCB technology or semiconductor technology. Examples of such transmission lines include microstrip lines, strip lines which have 2 ground planes and in between a strip, and coplanar waveguide transmission lines, which in principle do not require per se a ground plane at the bottom, and they are often used in semiconductor technologies. Another type of transmission line is a waveguide, either rectangular or circular. Now let's take a closer look at a transmission line. Well, this is the schematic representation of a transmission line. So it consists of 2 wires, a top one and a bottom one, and the 2 wires are at the input connected to a source which generates a voltage and a current. Now, along the transmission line we will assume that transverse electromagnetic waves can propagate either in the positive Z direction or the negative Z direction. If you want to know more about TEM waves, please check your undergraduate course on electromagnetics. Now, a transmission line is relatively long in terms of wavelength. Typically a few wavelengths, or can be even many tens of wavelengths. To solve for the unknown voltage and current at a particular position Z, we can either use electromagnetic theory, like by solving Maxwell's equation, or, and that would be preferred now, is to use Kirchhoff's law. But the problem is that circuit theory typically only works if your circuit is much smaller than the wavelength. Now, the question is, how can we still use Kirchhoff? Now, we could consider a small piece of length with the length of delta Z being much smaller than the wavelength, and try to model that as a lumped element circuit. Question is, how? Well, a possible implementation of that could be the following circuit. Let's consider this small piece of delta Z. The circuit could look like this. Why? Well, it accounts for a piece of length by including a series inductance. It accounts for losses that you might have in the metal, so it's represented by a series resistance. It accounts for the capacitance between the top and the bottom wire, and that's represented by a shunt capacitance. And between the wires there might be dielectric or other more complicated materials that could introduce losses as well, and that's accounted for by this shunt conductance. And at the input and the output of this small piece of wire we have the input voltage, input current, and the output voltage and the output current. Now, we can apply Kirchhoff's laws for voltage and current to this circuit. Let's first take a look at the voltage law, which states that the voltage at the input minus the voltage drop over the series resistance minus the voltage drop over the series inductance should be equal to the output, minus the voltage at the output should be equal to 0. Well, similarly for the current law, we have that the input current minus the current flowing through the shunt conductance minus the current flowing through the shunt capacitance minus the output current should be equal to 0. So we now have a set of two equations to solve. Now let us take a closer look at this set of equations. We recognize a voltage at the position Z and a voltage at the position Z plus delta Z. And if we would divide this first equation by delta Z and then take the limit of delta Z going to 0, then we all recognize a derivative to the voltage. And the same holds for the current in the second equation, and in that way we can define a set of differential equations which are coupled to each other. Note again that in this course we will assume that all the waves and the voltages and the currents, they are time harmonic. So that means that we work in the frequency domain, which is also represented by this differential equation. Now we can solve this set of differential equations, and the general solution, as you might expect, is a set of exponential functions. And in particular, the voltage can be represented by an exponential function which represents a wave propagating in the plus z direction, which is the first term in this equation, with an amplitude v0 plus. And we have a wave propagating in the minus z direction with a voltage amplitude v0 minus. And the same holds for the associated current waves. Now, gamma, which is the complex propagation constant, has two components, a real part, alpha, that's the attenuation along the line, and beta, which is the phase constant, which is related to the phase velocity of the wave propagating along the line. And gamma can also be expressed in terms of the equivalent circuit components R, L, G, and C. Another important parameter is the characteristic impedance of the transmission line, and that's the relation between the voltage amplitude of the wave propagating in the plus z direction and the current amplitude, and can also be represented in terms of the equivalent circuit model. Now let us look at the first application of a transmission line by terminating the transmission line at the end of the line with a termination, in this case an impedance ZL. Now the voltage and the current along the line are represented here in this set of equations where we used the characteristic impedance in order to represent also the current in terms of the voltage amplitudes. Note the minus sign, which is associated with the direction of the current of the wave propagating in the minus z direction. Now the termination is located at z is 0, and the termination sets a relation which we require to find the unknown amplitudes of the voltage waves and current waves. It defines the relation between the voltage and the current at the output of the transmission line. And in that way, we can describe a relation between the voltage amplitude of the wave propagating in the plus z direction and the voltage amplitude of the wave propagating in the minus z direction. So the incident and the reflected waves. Now, by rewriting this particular equation, we arrive at the relation between the reflected and the incident wave amplitude, which is shown here. And in that way, we can define a reflection coefficient, which is V naught minus divided by V naught plus, and is given by this equation. So it's the termination impedance minus the characteristic impedance divided by ZL plus Z naught. So that's the reflection coefficient at the termination. Now let's look at some examples. So a short, so we short circuit the end of the transmission line. In that case, ZL is 0, and we see that the reflection coefficient is equal to -1. In terms of an open, then ZL is infinite, and the reflection coefficient is 1. So in both cases, short and open, all the energy is reflected back in the line. If we terminate the transmission line with a load, which means that the termination impedance is exactly the same as the characteristic impedance, we see that the reflection coefficient is 0, and that's often, of course, what we would like to see. Now, the terminated lossless line has also the property that if the reflection is not 0, that the voltage along the line will fluctuate. And we can see that from this equation. So here I plotted the absolute value of the voltage along the line at a position Z, which we can write now in terms of the reflection coefficient. If we substitute Z is minus L, so at the location minus L, we find that the voltage can be written in this form, which means that the absolute value of the voltage has a minimum and a maximum if we walk along the transmission line. In particular, the maximum is given by the voltage amplitude V naught plus times 1 plus gamma. And the minimum is found by the voltage amplitude times 1 minus gamma. And the relation between the maximum and the minimum is called the voltage standing wave ratio, which is a very important measure, for example, for power amplifiers. But because if you would connect a power amplifier, for example, to an antenna, and the VSWR would be very high, then the maximum voltage along the output of the power amplifier could be higher even than the breakdown voltage, which would mean that your power amplifier would be seriously damaged. So the summary of this third web lecture is that we have introduced transmission line, and we found a model in order to apply Kirchhoff's law. We solved the telegraph equation. We looked into an application of a terminated lossless transmission line. We found the reflection coefficient, and we introduced the voltage standing wave ratio. Thanks for watching, and I hope to see you again next time. Welcome at this web lecture on power combiners or power dividers. Power combiners or power dividers have become a very important component in many wireless applications, mainly due to the relevance of beam steering antenna systems and the move towards microwave and millimeter wave frequencies. The objective of this particular lecture is to give a general description of power combiners. We're going to introduce a few concepts in this lecture and also in one of the follow-up lectures on power combining. We're going to provide some physical insights, so how does a combiner look like in practice, and we're going to discuss an example. Well, this is how a power combiner or divider could look like. This is a power combiner with 4 inputs, 1 output, or a divider with 1 input and 4 outputs, implemented in microstrip technology. We recognize 2 stages. So the first stage is an equal split power divider, and in the second stage we recognize an asymmetry. So we have 2 asymmetrical power dividers here. More on this will become more clear in this lecture and the follow-up lecture. Well, the general block diagram of a power divider, in this case an asymmetrical power divider, is shown here. So we have an input power P1. At the output of the divider we have, at port 2 we have an output power P2, and at port 3 we have an output power P3. And the fraction, the division fraction, is indicated by alpha. So alpha times the input power will flow to port 2, and 1 minus alpha, the input power will flow to port 3. In case of a symmetrical power combiner, the input power is split equally between the output ports, or in case of a combiner, both input powers are coherently combined into the output port. Now, a simple 2-to-1 combiner, 2 inputs, 1 output, can be represented by a 3-port representation in terms of a scattering matrix, shown here. Of course, we often want the input and output ports to be matched, so that means that the diagonal components of the scattering matrix would be equal to 0. In that case, from a mathematical point of view, if we require the network to be lossless, reciprocal, means mathematically that the scattering matrix needs to be unitary. Well, without going into too much details, the issue with the unitary condition of the scattering matrix is that, in fact, it cannot be met when the elements, the non-diagonal elements, are non-zero. So, in principle, the conclusion is a 3-port network cannot be lossless, reciprocal, and matched at all ports at the same time. So that means that we always need to find a compromise on one of the requirements for a combiner or a divider. Well, let us take a look at the most simple form of a power divider, which is the T-junction divider. It consists of 3 transmission lines which are connected directly to each other. A transmission line at the input with the characteristic impedance of Z0, and at the output ports we have other characteristic impedances, in this case Z2 and Z3. In addition, when you would connect 3 of these transmission lines at the interface, there will be spurious radiation occurring, and that is accounted for, can be accounted for, by adding a susceptance B to this circuit to account for the fringing fields. Now, if we would like the input to be matched of this power divider, then the input admittance, which is shown in the diagram here, which can be calculated from a parallel connection of the susceptance and the 2 output transmission lines, as shown here, should be equal to the characteristic admittance of the input transmission line. So it should be equal to 1 over Z0. In case that we neglect the fringing fields, we can say that the susceptance is 0 and that the input admittance simply reduces to this form here. Now let us take a look at an example of such a lossless T-junction divider. For a given source impedance Z0 is 50 ohm, let's try to find the output impedances, characteristic impedances of the transmission lines if we require an equal split divider ratio. Well, the solution is that first let us take a look at the input power which is delivered to the matched divider. The input power can be simply found from the voltage across the interface and the characteristic impedance of the transmission line. which in this case is 50 ohm, and the factor half again comes from the fact that we look at time average power of this time harmonic field and signals that we assume. The output powers can be found in a similar way from the voltage across the transition and the characteristic impedances of the connecting transmission lines. And we require that P2 and P3 are equal to half of the input power. Now, by solving these three equations, we find that Z2 and Z3 both need to be equal to 100 ohms, so 2 times Z0. If we look now at the output matching and the input matching of this divider, we see that first the input matching is indeed perfect, because looking at the input, we see an input impedance equal to 50 ohm, because we have two 100 ohm lines in parallel. However, if we look at the output, we see that the ports are not matched. If we consider the reflection coefficient of port 2 and 3, which are the same, we can calculate them from this equation, where the output impedance looking from port 2 into the circuit is a parallel connection of a 50 ohm line and a 100 ohm line, resulting in an equivalent impedance of 33 ohms. So from that we can see that gamma at port 2 but also at port 3 is equal to minus 0.5. Maybe we can solve the problem of the poor output matching of the T-junction power divider by adding series resistors at the junction of the divider, as shown in this figure. So we add, at each port, we add a series resistor, which is a lumped element with a value of Z0 divided by 3. And in this configuration here, we have assumed an equal split divider, and therefore all the characteristic impedances of the transmission lines are equal to Z0. The characteristics of this resistive divider, we can look at it by first considering the input impedance that we see if we look into port 2. We see first this series resistor, and we assume that port 2 is terminated with a matched load. So it's a series connection of this lumped element resistor plus the terminated transmission line. So means that the impedance is 4 times Z0 divided by 3. Using this knowledge, we can look into the input impedance looking into the divider from port 1, as indicated in this figure. We then see a series connection of a resistor with value Z0 divided by 3, and we have two parallel circuits, each with an input impedance of 4 Z0 divided by 3. So if we put that in parallel, we divide the value by 2, and we get, at the end of the day, we see that the input impedance looking from port 2 into the circuit is equal to Z0, so it's matched. And because of the symmetry, the same holds for the input impedance looking from port 2 or port 3 into this network. So that means that this resistive divider is matched at all ports, so that's good. Now, what's the problem? Well, let's look into it in more detail and try to derive the scattering matrix of this resistive divider. For that, we need to determine the voltages at all ports. The voltage at the central node can be found from the voltage at port 1 by considering that we have a voltage divider between one of the lumped element resistors connected to port 1, and we have, let's say, an equivalent impedance, which are the two parallel connections of the port 2 and port 3, including the two lumped element resistors. So that means that the voltage at the central node is found as V1 times this voltage divider, and at the end of the day it's equal to 2 times V1 divided by 3. From this voltage we can determine the output voltages V2 and V3, because again we see that the output voltage, for example at port 2, can be found from a voltage divider where we have the series resistor, the lumped element resistor, and we have the load across port 2. So that means that V2 and also V3 can be found from V, from the central node voltage in this way, and it appears to be equal to a half times the input voltage. So we have found the ingredients for the scattering matrix. So the scattering matrix looks like this. So it's half times this matrix, where on the diagonal we see zeros because all the ports are matched, and the non-diagonal elements are all equal to 1 times a half, of course. Now, it's matched, but there seems to be an issue, and that's power loss. Let's look into that a little bit more in detail. The power loss. The input power is P1 and can be found again from the voltage, V1, in this way, as we've done before. The voltages at port 2 and 3 we've also found, so from that we can also determine the output powers in this way, and we then come to the conclusion that the output power at port 2 is only 1/4 of the input power, and the same holds for port 3. Apparently 50% of the input power has disappeared, and of course this power is dissipated in the resistors. That means that this divider or combiner is not very popular, so you don't want to spend 50% of your power being dissipated in the resistors, but sometimes you don't care too much about it, and that often happens in IC design, where you can compensate for power loss by adding, for example, an additional amplifier, so to compensate for that. The resistive divider has the advantage that it's very compact and everything is matched, so that could be useful in certain applications. Now, to summarize this web lecture, so we introduced power combiners, power dividers, and we have shown that you can never have combiners or dividers which are lossless and at the same time have perfect matching at all ports, are reciprocal, and also have a perfect isolation between the ports at the same time. So we have to compromise. We looked into the simple T-junction divider and shown that that has a poor output matching. The resistive divider has a good output matching and input matching, but has 50% of loss. And in the next web lecture we will introduce an almost perfect component, I would say, and that's the Wilkinson power combiner or divider. Hope to see you back again. Welcome, my name is Bart Smolders, and in this web lecture we're going to talk about the Smith chart, which is a very useful tool in microwave engineering and antennas. The objective of this lecture is to provide you some history and use cases for the Smith chart. We're going to use it to visualize the reflection coefficient and the complex impedance, and we're going to show some examples. Now the Smith chart looks like this. It consists of many circles, curves, which are part of circles, many numbers on the Smith chart. Now it originates from the period during the Second World War, so it's in fact 80 years old already, and in that period there were no computers, so it was very useful to have a kind of approach, a tool to plot the complex reflection coefficient and to transform that directly to complex impedances, complex admittances, VSWR, etc., etc. Philip Smith invented the Smith chart, which is the result that we were going to discuss today. Now, the use of the Smith chart is to make a graphical representation of the complex reflection coefficient and the complex impedance, and it's very useful when you are designing a matching or tuning circuit, as we will see in one of the follow-up web lectures. The Smith chart might look rather complicated at first sight, but in fact it's not, because we're only plotting the complex reflection coefficient in the complex domain. Now this reflection coefficient gamma was already derived in one of the previous web lectures. It consists of a real part and an imaginary part, and because of that we can plot the real part along the horizontal axis in the complex domain and the imaginary part along the vertical axis. Now the absolute value of gamma is always smaller than 1, which means that all values of gamma fall within a unit circle with radius 1. Now as an example, we could plot the reflection coefficient in the complex domain, and it could look like this. But in fact, what would be interesting is to know the relation between the reflection coefficient of a circuit and the input impedance. Now, this was already derived in one of the previous web lectures, and this relation was given in this form, where Zin is the input impedance of a particular circuit at hand, and Z0 is the reference impedance, which is usually 50 ohm. Now, if you would plot the impedance values related to a particular reflection coefficient, you would see these kind of curves, which consists of circles and parts of circles. Now, what is it? What we see? Now, the normalized input impedance, normalized to the reference impedance, consists of a real part and an imaginary part as well. Now, the real part, if we would plot that in the complex domain of the reflection coefficient, so on the Smith chart, if we would keep this real part constant, would mean that we would walk along one of these circles, as indicated here in the Smith chart. So if we would vary the imaginary part, we would walk along the particular circle at hand with a constant real part of the input impedance. Similarly, we can keep the imaginary part constant, and then we would move along these curves, which in fact are parts of circles, which extend the unit circle of the complex reflection coefficient. In all cases, we are going to consider in this web lecture, we will assume that the reference impedance Z0 is equal to 50 ohm, which means that if the input impedance is exactly equal to the reference impedance, we would be at the center of the Smith chart in the middle. Now let us take a closer look at some examples. One of the most simple examples could be a short circuit where the input impedance is equal to 0. The associated reflection coefficient would be equal to -1. So that means that this particular point would pop up at the left side of the Smith chart along the horizontal axis. In case of an open circuit, the input impedance would be infinite and the reflection coefficient would be +1. So we would pop up at the right side of the Smith chart, as indicated here, along again the horizontal axis. In case of a perfect matched circuit with an input impedance of 50 ohm equal to the reference impedance 50 ohm, we would find that the reflection coefficient is 0 and we would be at the center of the Smith chart, as indicated here. When we have a more complex impedance, so for example 50 minus J 100 ohm, we can easily find this point on the Smith chart. How? Well, best is to first consider the real part. So in this case the normalized value is 1, and we find the circle with a real part which is equal to 1, starting in the middle of the Smith chart, as indicated here by the red box. So we have to move along this circle. The reactance, the normalized reactance in this case, is equal to minus J2, which means that we need to find the curve related to a reactance of minus J2. And we need to move along this curve as well. Well, at the intersection of both curves, we find the particular point on the Smith chart, as indicated here. Up to now, we looked into the Smith chart by considering the input impedance and the relation to the reflection coefficient. Of course, it's also possible to plot admittances instead of impedances. So we would have circles corresponding to a constant conductance, or we would have curves corresponding to constant susceptances. By combining both the impedances and the admittances, we get a rather complicated Smith chart, as indicated here, where the red curves correspond to impedances, real and imaginary part, and the blue curves correspond to admittances. To summarize this web lecture, the Smith chart is a very useful tool to visualize the reflection coefficient and the input impedance or input admittance. It is used nowadays in many CAD tools, design tools, and measurement equipment like vector network analyzers. And we're going to use the Smith chart for the design of matching circuits. Hope to see you back next time. Welcome at this web lecture. We're going to talk about impedance matching, and in particular we're going to use lumped elements to perform this matching. Many applications require matching circuits. For example, a power amplifier which is connected to an antenna might not have the optimal impedance matching in between. So you could correct that by adding a matching circuit. The objective of this particular lecture is to first explain in more detail the need for impedance matching. Then we're going to talk about LC matching using inductors and capacitors, and we're going to show an example using the Smith chart. Now first let us consider this very simple circuit where ZS could represent the source impedance of a power amplifier, and ZL could correspond to an antenna. The power delivered to the load, to the impedance ZL, is found in this way. It's the real part of the complex voltage along the load impedance and the current through the load impedance, and then the complex conjugate of that current. We have to take the real part of it and divide it by 2 because we're talking about the time average power. Now the voltage along the load can be easily found by considering the circuit as being a voltage divider, and which sets a relation between the voltage along the load and the source voltage. The current through the load is simply found in this way. Now, by combining these 3 equations, we find that the load power, which is absorbed in the load, is found in this way. And if we take the real part of this expression, we find this relation where we have expressed the source and load impedances in terms of the real part and imaginary part, as shown here within this circuit. Now, when is now the power delivered to the load maximized? That's a good question. Well, if we have a function, in this case we have a function depending on RS, RL, XS, XL, we can of course look at the derivative of the function related to the load impedance and related to the load reactance. And if both derivatives are equal to 0, then we obtain an optimal, in this case a maximum, the maximum power delivered to the load. And that appears to happen when we have the particular choice that the real part of the load impedance is exactly equal to the real part of the source impedance, and when the imaginary part of the load impedance is equal to minus the imaginary part of the source impedance. And we call this conjugate matching. So the load impedance is the conjugate of the source impedance. Now let's go back to the case of a matching circuit. So as I already indicated, often you need to add a matching circuit between a load and a source. for example, the power amplifier connected to the antenna. Now, how to realize this matching circuit? One way to do it is to use what we call lumped elements, using inductors and capacitors. Now, an inductor is indicated by this symbol, and the input impedance of this inductor in the frequency domain is given by J omega L, as we all know from circuit theory. In a similar way, the input impedance of a capacitor is given by 1 over J omega C. Note that these lumped elements have an input impedance which strongly depends on the frequency. So when you design a matching circuit based on lumped elements, be aware that only at the design frequency you will get an optimal result. Now, when can we use lumped element matching? Now, this is an example of what we call a system in package. It was originally designed for Bluetooth. And a system in a package consists of many ingredients. So you recognize here SMD components, so surface mount devices, being inductors, capacitors. And in this case, the size of this SMD component is 0402, which corresponds to a length of 1 millimeter, so very small. We also observe 4 integrated circuits, which are being made with semiconductor technologies. These integrated circuits are, in this case, wire bonded to a substrate, which is the carrier of this system in package. Now, in this particular application, Bluetooth, which operates at 2.5 gigahertz, the wavelength is 12 centimeters, which is much larger than the size of the SMD components, because that was only 1 millimeter. So in this case, lumped element matching is really applicable. If we move to higher frequencies, then of course the size of the SMD component could be a larger fraction of the wavelength, and then lumped element matching will have limitations. The Smith chart appears to be a very useful tool in the design of LC matching circuits. And it's used also in many commercial tools, and you can also download yourself the Smith chart tool to perform LC matching. Now, suppose we want to match a particular complex load impedance to a source impedance, and the load impedance here is indicated by the black dot on the Smith chart. If we would add a series capacitor to this load, we would move along the circle with constant resistance, as indicated here in the Smith chart. If we would connect the load to a shunt capacitor, we would move along the circle with constant conductance, as indicated here by the green arrow in the Smith chart. If we add an inductor, in this case a series inductors, we would also move along the circle with constant resistance, but then in the other direction as compared to the capacitor, as indicated here by the purple arrow. Finally, if we would add a shunt inductor, we would again move along the circle with constant conductance in the direction as indicated here by the green arrow. Now, by combining these 4 options, we clearly see that we can move in any direction in the Smith chart, which means that we can match any load impedance to a source impedance, which is, of course, the goal of what we want to achieve with the matching circuit. Now, let us take a closer look at an example of LC matching. And in this example, we have an 100 ohm load and we want to match it to a 50 ohm source by using this matching circuit, and the design frequency is 1 gigahertz. Now, the first step to take could be to add a shunt capacitor, which brings us along a circle with constant conductance to another point on the Smith chart. And in this particular case, we want to move to the circle with constant resistance being equal to 1, because we want to match to 50 ohm. And then the normalized resistance of 1 is equal to a real impedance of 50 ohm. The second ingredient in this matching circuit is a series inductor. So we will move along the circle with constant resistance, normalized resistance of 1, which brings us back into the middle of the Smith chart, and which means that we have perfect matching. At the design frequency of 1 gigahertz, the values of this particular matching circuit are shown here. If we would simulate this circuit in a circuit simulator and make a plot, as shown here, of the magnitude of the reflection coefficient versus frequency, we clearly see that at the design frequency, 1 gigahertz, we have perfect matching. However, if we move away from the design frequency, the matching becomes worse, and that of course is related to the fact that the impedances of the capacitor and the inductor are frequency dependent. So only at the design frequency the optimal matching can be obtained. If you want to improve the bandwidth of such a matching circuit, if you want to make it more broadband, then you could add more components to create a more complex matching circuit. So what about conjugate matching of our example? Because we started this web lecture by talking about conjugate matching, and in that way we could have optimal power transfer. Does it also apply for the example that we just discussed? Now let's split this matching circuit in the middle and first look into the left part of the whole circuit, where we look into an inductor and the source impedance of 50 ohm in this case. Now the impedance of this circuit is exactly equal to 50 plus j 50 ohm. Looking at the right side of the circuit, we look into a shunt capacitor and the load impedance, which in this case was 100 ohm. Now the input impedance of that part of the circuit is equal to 50 minus j50 ohm. So indeed, it is conjugate matched, as expected, of course. Now, to summarize this web lecture, we've shown that lumped element matching can be used, but it's important that the size of the components, of the physical components, should be much smaller than the wavelength, else it simply does not work anymore. Now, the Smith chart appears to be a very useful tool for the design of matching circuits. We've shown an example of LC matching, and in the next web lecture, we're going to extend the concept of matching with lumped elements. We're going to extend it to matching with transmission lines. Hope to see you back next time. Welcome. In this web lecture, we're going to use distributed elements to perform impedance matching. Now, in the previous web lecture, we have used lumped elements, inductors and capacitors, LC components, to do matching. Matching of a load to a source. Now, in this web lecture, we will show that you can also use transmission line based elements, so distributed elements, to perform matching. Now, in particular, we're going to discuss in this web lecture Richards transformation. We're going to apply that to shunt stub matching, single and double stub matching, and we're going to illustrate it using an example. Now, first let us go back to the terminated transmission line, which we introduced in one of the previous web lectures already. So we have a line with length L, which is connected at the end to a load with an impedance ZL, a complex impedance. When we look into this line section of length L and we try to determine the impedance, the input impedance, then we have shown in one of the previous web lectures that this input impedance it's given by this equation, which in fact is a varying input impedance, since when varying the length L, we can change this impedance. So in fact, this is an impedance tuner. Now, let us take a closer look at some specific cases, and there we come to Rich's transformation. The first special case that we're going to consider is a short circuit, and the second one is an open termination. Now, the short circuit means that the complex impedance at the end of the transmission line is equal to 0, which transforms the input impedance of the line section, which is shorted at the end, to this equation. So it's J times Z naught times tangents beta L, which can also be written as J large omega times Z naught. And that looks already similar to the impedance of an inductor, so J omega L. Now, in a similar way, we can calculate the input impedance of a transmission line which is open at the end, at the termination, and then we get this equation where the input impedance can be written in terms of the Z naught divided by J large omega, which again already is very familiar to us because it looks like 1 over J omega C. Well, in fact, these equations show that we have an equivalence, and the equivalence, the first equivalence, is the equivalence of an inductor with an impedance J omega L is equivalent to a transmission line with a certain length which is shorted at the end. And similarly, we have the equivalence of a capacitor with an impedance of 1 divided by J omega C, which is an open circuit transmission line with a length L. Now, in the particular case, and that's what we assumed already in these figures, that the length is equal to lambda over 8, we get the feature that since beta is equal to 2 pi over lambda, with the length lambda over 8, we see that the large omega, which is tangents beta L, simplifies to 1, which means that in the figures that we've shown here, we really have the one-to-one correlation between the lumped element, LOC, and the short-circuited or open-circuited transmission line. Now with Rich's transformation, we have the equivalence of LC lumped elements in terms of transmission lines with a certain length and open or short-circuited. And we can use the same philosophy as that we have introduced for lumped element LC matching in the previous web lecture, where we used the Smith chart to indicate that you can transform from any point in the Smith chart to another point by using one of these series or parallel lumped elements. And by using Rich's transformation, we can do the same with transmission lines. But with transmission lines, we have more flexibility because we can also add series sections with a certain length. Now let's have a closer look into this option, and then we come to the topic of shunt stub matching, and we will start with the single shunt stub matching circuit. It's shown here. We have a termination with a certain complex impedance that we want to transform to a transmission line with the characteristic impedance of Z naught, for example 50 ohm. In between, we add a transmission line with a length D with the same characteristic impedance, Z naught, and at the end of this transmission line, we have the termination, and at the beginning of this transmission line, we have a shunt stub, which can either be open or short-circuited. And the shunt stub has a length L to be determined. Now, if we look into the terminated transmission line with length D and have a look at the input admittance, we can write it in this form. So it has a real part, GT, and an imaginary part, BT in this case. And the complex admittance, or the complex impedance, can be calculated with the well-known equation that we derived already in one of the previous lectures. And by tuning the length D, we can vary the impedance or admittance. Now, that brings us to the philosophy that we want to use for single-step matching. And the idea is first to make sure that the real part, GT, is exactly equal to the characteristic admittance of the connecting transmission line. So GT should be equal to Y0 or equal to 1 over Z0. And we can fulfill this requirement by selecting the right length D. So that's the first step. Now, the second step is to tune out the imaginary part, so BT. And we can do that by adding this shunt stub and make sure that it's exactly the opposite of the imaginary part of YT. And we can fulfill this requirement by selecting the length L of the stub in such a way that this is fulfilled. Now this procedure can be illustrated using the Smith chart, and let's use an example to show how this works in practice. Now, first the Smith chart, already shown a couple of times before. The example that we have at hand is the following. We have a load impedance, which is complex in this case. So we have 100 minus J60 ohm. And this point in the Smith chart is located over here. Next to that, we want to match this complex load to a transmission line with a characteristic impedance of 50 ohm. And that's the middle of the Smith chart. That's the point shown over here. Now the first step in applying the single stub tuner is to move towards the circle where the admittance is equal to 1 over 50. Because if we walk around the circle, we can reach the middle point of the Smith chart, as indicated here. So by selecting the line length D in a proper way, we can move from the original point in the Smith chart towards this circle. And the particular value that we have to use is 0.125 lambda in this case. The next step is to add the shunt stub. And in this case, we are going to use a shorted shunt stub with a certain length L. In order to move towards the middle of the Smith chart, we need to select a length of 0.118 lambda. And in that way, we are again in the middle of Smith chart, which means that we have created a matching circuit from the 50 ohm transmission line towards the complex termination. Well, how does a circuit look like? If we would simulate it in, for example, a circuit simulator like ADS, we would see that with this particular values that I have indicated here, with the design frequency, for example, of 1 gigahertz, we would end up with this curve. So exactly at 1 gigahertz, we have perfect matching. But because the line sections, of course, have an input impedance which is frequency dependent, so only at the design frequency we have perfect matching. If you go off the design frequency, you see that the input reflection coefficient of this circuit is increasing, which means in practice that this circuit will have a limited bandwidth. And the bandwidth could be defined as indicated here. Next to single shunt stub matching, we can also extend it to double shunt stub matching, as indicated in this figure. So we again have a line section with the length D, but now we have 2 stubs, which can be either open or short circuited stubs with a certain length, L1 and L2. The features of this double shunt stub tuner, in fact, are that you don't need to vary the line length D per se. You can do it, but you don't have to do it. You can reach a lot of impedances in the Smith chart by only adjusting line length L1 and L2. For that reason, it's easier to implement in practice, and you also see this concept back in many commercial tuners which are in the market, for example, for load pool measurements and those kind of applications. However, by having a fixed D and only varying L1 and L2, not all possible values in the Smith chart can be reached. So it has a limited range in matching. So to summarize this web lecture, we have first introduced the transmission line equivalence of LC components with Richards transformation. On top of that, we can also add additional line sections, and we have applied that to the case of shunt stub matching. And we have seen in the example that the Smith chart is again here a very useful tool to visualize the concept of matching. Thanks for watching, and hope to see you back in the next web lecture. Welcome at this web lecture where we're going to discuss microwave filters. Microwave filters are another application of transmission line concepts, and microwave filters are very useful. For example, they can be used in receivers to reduce the linearity requirements by suppressing out-of-band interference, or they could be used together with transmitters to suppress out-of-band spurious components that might occur. The objective of this particular lecture is to first look into some lumped element filter concepts. Then we're going to transform two transmission lines by using the so-called Koruda's identities. And we're going to look into two specific filter concepts, the low-pass filter and the coupled line bandpass filter. And I will show some examples, including simulations. Now, first let us have a look at lumped element filters. Well, these four filters, which are shown here, are quite well known. With an inductor, you can create a low-pass filter. Why? Because a DC current would simply flow through an inductor. So at low frequencies, the inductor is a low pass, has a low pass characteristic. At high frequencies, the impedance of the inductor would increase finally to very high value, and that would stop signals to be transferred through the inductor. So that's why we have a low pass filter. Well, for capacitor, it behaves as a high-pass filter, and by combining a capacitor and an inductor in series or in parallel, we can create a bandpass or band-stop filter. These concepts are well known from circuit theory. There are many books about how to design such a filter, even with much more branches. Now, in one of the previous web lectures, we have introduced Richards transformation, where we could simply transform an inductor and a capacitor into a transmission line equivalent circuit. So an inductor could be represented by a shorted stub, where the length of the stub was lambda over 8, and a capacitor could be represented by an open stub, also with a length of lambda over 8. Now, the procedure could then be to design a filter is then the following. First, design a lumped element circuit using LC components, then transform using Richards transformation into a transmission line version. If we do that, for example, let us consider a low-pass filter consisting of two inductors and a capacitor, as shown here. If we would apply Richards transformation, the equivalent transmission line circuit would look like this. So the shunt capacitor would be represented by a shunt open stub, which is okay. It's easy to implement, for example, in microstrip technology. The series inductors would be represented by stubs, shorter stubs, but then placed in series with the input and output transmission line. Well, that causes some troubles if we want to implement it in a practical technology. For example, if we consider a microstrip technology, as shown here, a microstrip technology where you have a microstrip line which is placed on a dielectric material with a certain thickness, and underneath there's a ground plane, a metal ground plane. The electric field of the propagating TEM mode along the transmission line in a microstrip technology would be let's say flow from the top microstrip line to the ground plane, as shown here in this figure, which means that it's almost impossible to realize the series stubs in a microstrip technology. So we like to avoid using series stubs. Now, how to do that? Now, a solution for this problem is provided by the Karuda's identities. Karuda's introduced these identities in 1955, a long time ago, and he published that in his PhD thesis. The Karuda identities consist of 4 identities, but let's have a look at the first one, which is one that we're going to use also in an example. We have a series inductor which is connected to a transmission line with a length L with a certain characteristic impedance, and we can transform that using the Karuda identity to a transmission line with the same length but with another characteristic impedance as indicated here in the figure, and a shunt capacitor. And the value of the inductor represents in fact a series shorter stub with a characteristic impedance given by Z1, and the shunt capacitor on the other side, on the right side, represents a shunt open stub with a certain characteristic admittance. Now, the line that is used connected to the series inductor and the shunt capacitor should have a length of lambda over 8, and the value of n squared is given here in this figure as well, and can be simply calculated by the characteristic impedances of the series shunt stub and the characteristic impedance of the lambda over 8 line. Another Karuda identity is shown here, and in fact there are several other identities that you can find in the book. Now let us have a look at a specific design of a low-pass filter that could be implemented in a microstrip technology, so avoiding series stubs. The specifications that we are going to look at are given here. So we're going to consider a maximally flat filter, third order filter, NS3, with a minus 3 dB point, a roll-off point at 10 gigahertz. The reference impedance is 50 ohm, and the input and output port impedances are also 50 ohm. Now, the first step is to create a lumped element LC low-pass circuit. Now, this can be found in many books for the specific filter characteristic, and the values of such a lumped element low-pass filter are shown here. So we need 2 inductors and a capacitor with these specific values. In order to construct a microstrip version, we need to transform the lumped element filter using Rich's transformation to a transmission line version, which we have seen before. So we have 2 series shorted stubs, and we have, in between we have an open shunt stub. The values of the characteristic impedances of the stubs can be easily calculated by inserting the frequency that we're going to use, which is in this case 10 gigahertz, and then we find, for example, that the series stub impedance, characteristic impedance, should be 50.3 ohm. The next step is now to apply Karuda's identity to get rid of these series stubs, which are not possible to implement in microstrip technology, as we discussed before. Note that the stubs, as I showed before, should have a length of lambda over 8 at 10 gigahertz. Then we're going to apply the Karuda identity, and we do that by first adding two sections equal to lambda over 8 at the input and output of the filter. We can always do that because these are sections with a characteristic impedance of 50 ohm. So nothing will change in the performance. By doing that, we recognize the first Karuda identity, and we can apply the equations that we just have discussed. By doing that, we transform this circuit, this transmission line circuit, into this circuit where we have three shunt stubs which are connected through two lambda over 8 lines. And the values, the specific values of the characteristic impedances of the stubs and the transmission lines can be calculated by using the value of n squared and by applying the equations that we have just shown. The frequency response of this low-pass filter is shown in this picture. The red curve represents the performance of the original lumped element filter, and the blue curve is the transmission line version. We clearly see at 10 gigahertz, as expected, a minus 3 dB roll-off, and we clearly see a low-pass behavior. We also observe at higher frequencies that the transmission line version behaves differently. Now, that was for low-pass filters. Let's now take a closer look into another type of filters, which is often used in microwave applications, which is the coupled line filter. The coupled line filter is a filter which we can use to create a bandpass behavior. In this particular example, we have two resonators with a length each of lambda over 2, so half a wavelength. And these two resonators together are coupled to an input line and an output line. And in this way we create, in fact, three coupling pairs, as you can see in the picture, varying from KS1 to KS3 in this case. But of course we can have many more sections. The coupled pair resonators, they provide even and odd modes. So even and odd modes can propagate along these coupled pairs. And associated with even and odd modes, we have even and odd mode characteristic impedances. A single pair, a coupled pair, can be represented by an equivalent circuit, which is shown here, which is a combination of two open series stubs. In between there's a transmission line with a length of lambda over 4. And the characteristic impedances of the lambda over 4 stubs and the transmission line are provided here. More details about how to exactly determine the characteristic impedances of the stubs and the transmission line, so the design equations are provided in the book. Now let us take a closer look at coupled line filters by looking into an example with the following specifications. So we're going to look into a Chebyshev equal ripple filter with the 3 dB ripple maximum in the passband. We're going to use two resonators, so NS2, and we're going to design the filter to be centered around 28 gigahertz with a 20% bandwidth, so 10% on each side. If we design such a filter using the equivalent circuit, which I just introduced, the design in ADS would look like this. And you recognize the three coupled pair sections, and in the middle you recognize one of these coupled pair sections having two open stubs connected in between by a lambda over 4 transmission line. And that's also indicated in the simulator that E, which represents the electrical length, in this case is 90 degrees, so it's lambda over 4. If we simulate this circuit in ADS, we get the following response in terms of frequency. We clearly see the filter is centered around 28 gigahertz, and we recognize that the bandwidth is indeed 20%. And the ripple, the maximum ripple in the passband is exactly 3 dB as well. So to summarize this web lecture, we always start with a low-pass lumped element prototype. Then we transform it using Richards transformation and Karuda's identities to a transmission line version that we can implement in a certain technology, like a microstrip technology. In this web lecture, we looked into two specific examples, a low-pass filter and a bandpass filter, and checked for the book for more detailed design equations. Thanks for watching this web lecture. Welcome again. Welcome at this introduction web lecture on antennas. And this web lecture is in fact the first in a series on antennas, theory and applications. So today we're going to look into the following topics. So first, what is the source of electromagnetic radiation? Then we're going to look in some history of antennas. We're going to discuss a few examples of antennas, and we're also going to introduce the coordinate system that we're going to use throughout all the web lectures on antennas. At the end, we're going to define also the field regions around an antenna. Now, let's start with a well-known configuration. So suppose we have a static charge, not moving, with the charge density Q. If we look at the electric field at the distance r from this charge, then we can apply Coulomb's law, as you might remember from your bachelor course on electromagnetics. And Coulomb's law states that the electric field is given by this equation. So it's directed in the radial direction, which is indicated by this unit vector. And more importantly, it shows a 1 over r squared dependence. So when distance increases, it has this 1 over r squared dependence with distance. Now, if this same charge is moving, so in fact it's accelerating, so it's, in this case we show an oscillating charge, oscillating between 2 points. Then if we again look at the distance r from this charge, then, as we will prove in the upcoming web lectures, the electric field far away from this accelerating charge has this type of form. So in this case it looks quite similar to Coulomb's law, but in fact the main difference is that it has a 1 over r dependence far away from the antenna. So instead of a 1 over r squared, we now have a 1 over r dependence. And in addition, this accelerating charge also generates a magnetic field. So we have an electric and a magnetic field, both with a 1 over r dependence, and as a result we have radiation of energy. So energy is propagating away from the accelerating charge. So keep in mind, acceleration of charges is the source of electromagnetic radiation. Now, some history of antennas. Well, the first kind of antenna experiments were done by the Italian scientist Galvani. He did it in the 18th century, and he has a lab where he conducted experiments with wires and frog legs. And the frog legs were in fact a microwave receiver. So if there was electromagnetic energy, for example from lighting, received by the wire antenna, then there would be a current flowing on this antenna, and the frog leg would act as a receiver, and if there was any current detected, then the legs would move. So that would be a kind of indication that there are signals received by the antenna. Well, in about 100 years later, Maxwell formulated his Maxwell's equations, and that were the kind of theoretical foundation of the antenna theory. And a couple of years later, in 1887, the German Hertz, he did his experiments and he made a real transmitter and receiver system. So he showed over a distance of 5 kilometers at the frequency of 430 megahertz that indeed you could transmit electromagnetic energy from a transmitter to a receiver. Well, it was about 14 years later that Marconi, he was more like an engineer, Italian engineer, and he commercialized this invention of Hertz, in fact. And he performed the first transatlantic wireless link in 1901. There are several types of antennas, and in this picture you see 4 commonly used antenna types. You probably know them from practical applications. So the first antenna type shown here is the reflector antenna, which is used in many applications. So for example, this application is for radio astronomy, to investigate the universe. Reflector antennas have typically a large receiving aperture, and in that sense they can work with very weak signals. Another antenna type very commonly used is the wire antenna, for example to receive FM radio signals. Wire antennas are used in your car, on radios, as I indicated. Another antenna type is the horn antenna, which is also an example of an aperture antenna, similar to the reflector antenna. We also call it an aperture antenna. And the horn antenna is often used as a feed in a reflector antenna, so to illuminate the reflector or to receive the receiving signals from a reflector antenna. Now these 3 types are very conventional, you could say. They have been used throughout the past 100 years. More modern antenna types are often printed on PCB technology, and an example is the microstrip antenna, which is in fact a copper patch which can be printed on as I said, a PCB material, or can even be integrated if we go to much higher frequencies in a semiconductor technology, so it could be integrated on chip even. Now, throughout the course we will discuss many more examples of antennas, of course. Nowadays we also see more complex antenna systems, so not only the passive antennas but also active, more complex antenna systems, and a nice example of that is the phased array antenna, and an example is shown here. This is a prototype which was built about 20 years ago for the square kilometer array, also for radio astronomy. And what you see here is that it consists of many small antenna elements, and each antenna element is connected to electronics at the backside. And by this combination of passive antennas and electronics, it's possible to do beam steering. So the antenna can electronically steer the beam without any mechanical movement. Now, traditionally phased arrays are expensive, power hungry, and are used in professional applications like for radar or radio astronomy. But we see now a trend towards the application of phased arrays for wireless communication. And with the introduction of 5G, especially 5G operating at higher frequencies, at millimeter wave frequencies, at Ka band, that's about 30 gigahertz, we see that phased array technology is coming into the commercial applications. And in this picture you see a prototype that we developed with our PhD students of a base station for 5G millimeter wave, and it's a phased array and which can electronically perform beam steering, as we have seen also in the professional applications. Now we're going to talk more about applications including phased arrays throughout the upcoming web lectures. Now let's go back to the starting point, the theory, and we're going to introduce the theoretical framework for antennas, and of course we have to use a coordinate system to do that. Now we're going to use spherical coordinates as shown here. So in this XYZ coordinate system we have spherical coordinates indicated by r, theta and phi. And at the point P, we can identify 3 unit vectors. And these unit vectors are indicated by ur, u theta and u phi. So mind that the notation in several books of unit vectors might be different from this notation. But in these web lectures here, we're going to use this notation. Now, antennas are a kind of connection between electronics and the free space. So apparently there is a transformation from guided waves into radiated waves. And as indicated here in this picture, we have some kind of generator that generates a signal, and that signal can be transported over a transmission line, for example as a guided TEM wave. And the antenna then converts this guided wave into an unguided or radiating wave, a spherical wave that propagates away from the antenna. Now in this picture you see the orientation of the field. So this is a kind of situation at a particular time moment t is t0. And throughout the web lectures on antennas we will assume again that we have time harmonic fields, similar to what we did in the transmission line theory. If we consider an antenna, in this case a dipole antenna with a length L and fed with some voltage at the input, we can distinguish several regions around the antenna, as you can imagine. If you're very close to the antenna in the near field, if you put your hand, for example, very close to such a wire antenna, then probably the impedance will change of the antenna. So it will really affect the impedance of the antenna. If you're very far away, then of course this will not happen again. Now, in between being far away and being in the near field, we have defined a Fresnel region, which is kind of intermediate region, where we do not have the impact on the impedance anymore, but we also do not have the 1/r field dependence that we talked about earlier. Far away from the antenna, we talk about the far field region. And these 3 regions are also indicated by numbers, so you can calculate it as indicated here. So the transition between the near field and the Fresnel region is indicated by this equation, and the far field starts at the distance 2L squared divided by lambda naught, and L is the length of the antenna in this case, and lambda naught is the wavelength in free space. Now, as a summary of this web lecture, we have shown that the acceleration of charges is the source of electromagnetic radiation. We introduced several antenna types, ranging from wire antennas to aperture antennas like horn and reflectors, and even phased arrays, so more complex beam steering antennas. We talked about field regions, and we introduced the coordinate system. Hope to see you back in the next web lecture. Welcome. In this web lecture we're going to talk about antenna parameters. And antenna parameters are important since they indicate the quality of the antenna. And antenna parameters are commonly used in system level analysis, for example to determine the maximum distance of a communication link. So the topics we're going to address in this lecture are, first we're going to introduce the pointing vector in the far field. We're going to talk about the radiation pattern of an antenna, and we're going to introduce the directivity and antenna gain, and finally we will introduce the effective antenna aperture. Now let's consider an antenna, in this case a kind of dipole antenna located at the center of our coordinate system and fed by some voltage. And in the far field we have a point P, which is indicated by the position vector r. And at large distance from the antenna we can write down the electric field as a summation of two components. So one component E theta in the theta direction and a component in the phi direction, E phi. So there's not a component in the radial direction, since we assume that in the far field we have a TEM wave, which means that it's locally a plane wave, propagating in the r direction with two components, as indicated here. Now these two components, and we will of course derive these expressions later on in the course, can be written in the following way. So first, E theta can be written as a multiplication of some amplitude dependent on theta and phi times an r dependence, and the r dependence consists of the exponential term with a phase term minus j k naught r, and k naught is the wave number in free space and is equal to 2 pi over lambda naught, and lambda naught is the wavelength in free space. In addition, we have again the 1 over r dependence, as we already introduced in the previous web lecture. Now, similarly, we can define the theta component. So E theta looks like this. Again, we have the phase term and the 1 over r dependence. Now, in the far field, we assume a TEM wave, which means that the magnetic field is perpendicular to the electric field. And mathematically, we can write that like this. So the H field, the magnetic field, is 1 over Z naught times UR outer product with E. So it's perpendicular to E. And the 1 over Z naught term, the Z naught is the free space impedance. So that relates the electric and magnetic field. And the free space impedance is approximately equal to 377 ohm. Now, an important measure that we need to introduce is the Poynting vector, and you can see the Poynting vector as something equivalent to power, which we already discussed when we talked about transmission lines. So power can be expressed in terms of voltages and currents, and the Poynting vector is expressed in terms of the electric and magnetic field. So the Poynting vector is in fact the power density, the directive power density of a propagating wave. And it can be written in this form. So it's the time average again of the time domain Poynting vector. And we assume again that we have time harmonic signals and fields. So that's why we take the time average. Now this time domain Poynting vector is the outer product of the electric field and the magnetic field. And of course, since we work with time harmonic fields, we want to transform that to the frequency domain. And if you work out this integration in time, then you can show, similarly to what we did in transmission lines, you can show that you can express it in this way. So it's 1/2 times the real part of the frequency domain electric field outer product with the frequency domain representation of the magnetic field. Note that we need to take the conjugate of the magnetic field. So the time average Poynting vector is derived in this way. Now, if we substitute again the relation between the magnetic and electric field in the far field region, so it's this TEM relation, we can simplify the Poynting vector, the time average Poynting vector, in this way. So it's then 1 over 2 Z naught times the absolute value of the electric field squared. And as you can see, the power flows in the R direction. So it's really radial energy flowing away from the antenna. And it's expressed in watt per square meter. Now let us consider the coordinate system as shown here. So we assume an antenna located at the origin of this coordinate system. And at the distance from the antenna, far away from the antenna, we can define a small piece, a small surface, ds, and ds can be written in terms of what is called the solid angle, so omega. So ds can be written as r squared times d omega, and d omega is sine theta, d theta, d phi. Now, the power flowing through such a small surface, the power density, as you can say, can be expressed in this way. So the power density, which is a function of theta and phi, is given by the absolute value of the Poynting vector times r squared, and is also expressed in terms of watt per square meters. Now, if we normalize this power density by its maximum value, we obtain the normalized radiation pattern, and this normalized radiation pattern is a visualization of the properties of an antenna. So you can make a very nice plot of it. Now, this is shown in the next example. So this is a two-dimensional radiation pattern shown here of a particular antenna with a certain aperture size. So you observe along the horizontal axis theta in degrees, ranging from minus 90 degrees to plus 90 degrees. And we have expressed the radiation, the normalized radiation pattern in terms of decibels in dBs, ranging from 0 in this case to minus 50 dB. Now, we observe a main lobe, and that's the main working region of the antenna, where a lot of power is radiated. And we observe side lobes. So, for example, the first side lobe, but we also have second, third, etc. side lobes. Another important measure of the antenna is the half power beam width, which indicates the region where at least half of the power density is available in a certain region. And this is an important measure which is often used in communication systems. Now, besides two-dimensional representations, we can also have three-dimensional representations. So again, we use decibels, but here we also introduced UV coordinates, where U and V are related to theta and phi and are very convenient to use. The circle that you observe is what's called the visible space. So the circle is indicated by the region where U squared plus V squared is smaller than 1, and that's, as I said, related to the visible space. Now, apart from the normalized radiation pattern, we have other parameters which are important, and the first one is the directivity function. And the directivity function is the power density from the antenna divided by the power density what you would have if you would have an isotropic antenna. So an isotropic antenna radiates the same amount of energy in all directions. So the power radiated, transmitted power divided by 4 pi is then the power density from this ideal isotropic radiator. So we always relate the power density from a real antenna to the power density from an isotropic radiator. Now, the directivity is the maximum of the directivity function and can be calculated in this way. Now, besides directivity, we often use the antenna gain, and the antenna gain compensates the directivity for any losses that you would have. For example, ohmic losses that you would have in the metallic structures of your antennas. And the radiation efficiency is in fact the transmitted power divided by the actual input power that you provide to the antenna. Both the antenna gain and directivity are expressed in dBi, and the I stands for isotropic. So it's relative to an isotropic radiator. Now, another parameter which is important is more important in the receiving case of the antenna. So in the receiving case of an antenna, the antenna captures a part of the incoming field, absorbs it and translates it into a guided wave, which is then an input signal for a receiver, which is built in electronics. Now, there's a relation between the effective antenna aperture and the gain, and we will derive it later on in one of the web lectures. is given by this expression. So it's the gain times lambda naught squared divided by 4 pi. And the free space wavelength, lambda naught, as you might know, is equal to c divided by f, where c is the speed of light, which means that the effective antenna aperture scales with 1 over f squared, so 1 over the frequency squared. And this is also the reason why the communication distance, when we move up in frequency to higher frequencies, for example in 5G millimeter wave, that's the reason why the communication distance decreases with 1 over f squared if we move to higher frequencies. Now, in summary, we have introduced first the pointing vector, then we looked into the graphical representation of the radiated power using a normalized radiation pattern. We have introduced the directivity and antenna gain, and we have introduced the term dBi, so relative to isotropic elements, and we have introduced the effective antenna aperture. Well, thanks for watching and hope to see you next time. Welcome again. Today we're going to talk about the link budget, and in particular we're going to introduce the radio and radar equations. And as you know, antennas are part of complete systems, for example a wireless communication system or in a radar system. And we can apply the antenna parameters that we introduced in one of the previous web lectures in such a system. And that results in these famous radio and radar equations. Now, the objective of this lecture is to introduce first the radio equation, then we're going to show an example of such an equation. In particular, we're going to talk about Bluetooth. And finally, we're going to derive the radar equation. Now, let's consider first a general wireless communication system. And it's illustrated here. We have a transmitter, that's general electronics, a power amplifier, generating a power PT. And this power is transferred to a transmit antenna, and the transmit antenna has the property of a gain GT, and transmits the electromagnetic energy into free space, and the wave is propagating over a distance r towards a receiving antenna. And the receiving antenna is characterized by a gain, GR, and an effective area of the receiving antenna. The receiving antenna again transforms the received power into power that is input for a receiver. And the received power is PR. Now, let's see if we can derive the radio equation based on this system. First, let us look at the power transmitted by the transmit antenna at the receiver. So we have a spherical wave expansion, and the received power at the receiver is then given by the transmitted power, PT, times the gain of the transmit antenna, divided by this 4 pi r squared term, which is the spherical expansion of the transmitted wave. And the power density at the receiver is expressed in watts per square meter. Now, part of this power density is absorbed by the receiving antenna, and the part that's absorbed is of course characterized by the effective area of the receiving antenna. So it's a multiplication of the power density times the effective area of the antenna. And the effective area of the antenna can be rewritten in terms of the gain of the receiving antenna, like we did in one of the previous web lectures. And then we get this term, lambda naught squared, divided by 4 pi r squared. And that's in literature called the free space path loss. And, well, you would think of loss. Is it loss? Because we assume that we have a lossless propagation channel. No, in fact, it's not loss, but it's a kind of perceived loss because the effective area of the receiving antenna scales with frequency. So for a given gain of the receive antenna, the effective area becomes smaller and smaller once you go to higher frequencies. But remember, it's not loss in a physical sense. Now, Having said that, from this equation we can determine the maximum range, R max, so that's the communication range. And an important parameter in this equation is the receiver sensitivity, so the minimum power that is required by the receiver to be able to demodulate the received signal. And that's given by the specific wireless communication system at hand. Now let's take a look at an example. Bluetooth, well known to you all. Bluetooth is available in your phone, in your laptop, etc. And Bluetooth can be used for short-range communication, like in-house. The specifications of Bluetooth are provided here. So the frequencies between 2.4 and 2.48 gigahertz in the ISM band. In Bluetooth, typically we use omnidirectional antennas. Let's assume the gain is 1. The output power is 1 milliwatts, so that's equal to 0 dBm, and the minimum receiver power that is required to be able to demodulate the Bluetooth signal with a low bit error rate is minus 70 dBm. Now, using these specifications in the radio equation, we can derive the maximum range in case of Bluetooth, and we have to use the wavelength in free space, which can be calculated in this way. So it's 12.3 centimeters. Substituting that in this equation with all the other parameters, we get a maximum range of 30 meters. Now, 30 meters is in case of an ideal propagation channel without any obstructions or whatever. And in practice, you can imagine that a range of 10 meters makes sense in case of Bluetooth. Let us now look at the radar equation in radar systems. And radars are commonly used for military applications, for example, but nowadays also we see a lot of radar systems in cars for autonomous driving, for example. Now, a radar system could look like this. So we have a transmitter, a receiver, we have far away from the radar we have a target. It could be another car, for example. Now, the radar system itself consists of a transmitter and receive electronics and consists of a transmit and receive antenna. And often in radar, for example in pulsed radar, which is commonly used in military applications, the transmit and receive antenna are identical, are the same. They are shared over time. In FMCW radar, which is commonly used in automotive radar, we use separate antennas. Now, the radar transmits a certain amount of electromagnetic energy, and waves are propagating towards the target, and the target reflects part of this energy back towards the receiving antenna of the radar and is again demodulated. And in this way we can process the received data and determine whether there's a target, whether it's moving or not. Now let's assume again that the distance between the radar and the target is given by R again. Now the radar equation is derived in a similar way as the radio equation. So we first look at the power density at the target, which is identical as in case of the radio equation. But the target is of course not a receiving antenna, but is characterized by a radar cross-section. And the radar cross-section, sigma in square meters, is a measure for how much energy is reflected back towards the radar. The received power then at the radar is the power density at the target times the radar cross-section of the target times the effective area of the receiving antenna divided by 4 pi r squared because of the spherical expansion again of the wave that is reflected back by the target. Now we can again use the equation for the effective area. We can write it in terms of lambda and the gain of the receiving antenna, and we get finally this expression. So from this expression we can determine the maximum range by rewriting this equation. And the maximum range is determined in this way once we also know the receiver sensitivity. So that's the minimum power that is required by the receiver in order to be able to detect a target out of the noise. Now, to summarize, we introduced the radio and radar equations, which can be used to determine the maximum range of a system under ideal conditions. So a more detailed model should be used if you really want to include a propagation channel which is realistic, both for radar and radio. Thanks for watching and hope to see you next time. Welcome again. Today we're going to talk about the antenna impedance. And antennas, of course, are used to radiate electromagnetic energy, but antennas are also connected to electronics and to transmission lines. And therefore it's very important to determine a circuit representation of antennas. And that's what we're going to do in this web lecture. Now, the objective of this web lecture is first to introduce the equivalent circuit of an antenna. Then we're going to derive an expression for the total radiated power, which is required to be able to calculate the input impedance of an antenna. And finally, we're going to look into the input reflection coefficient. Now, let us first look at an antenna. Well, for example, this dipole antenna, which is fed at the center by some voltage. Now, the equivalent circuit could look like this. So the antenna is connected to a generator with a certain generator voltage and an internal impedance. In this case, we assume a real part, but it could also be complex in general. Now, the antenna itself is represented by a complex impedance with a real part and an imaginary part. And the real part is again consisting of two components. So the radiation resistance, and that's a measure of how much energy is really radiated. So it's not a loss per se, but it's something that you want. The antenna should radiate. But the real part also includes a loss term. So these losses, RL, are related, for example, to ohmic losses that you might have in metal conducting surfaces which are part of your antenna, or dielectric losses, as to say. Now the imaginary part is related to the near field and is related to the stored energy around the antenna. And often the real part, the imaginary part at resonance of the antenna is close or equal to 0. Now, the most relevant part of the antenna impedance is, of course, the radiation resistance, since it's a measure of how well an antenna works. And the radiation resistance can be determined from the total power that is transmitted by an antenna, if we consider a transmit antenna, and the current flowing through the antennas, as shown here. The total power radiated by the antenna can be calculated by considering a transmit antenna and far away from this antenna determine the total power radiated over a sphere around the antenna. And it can be expressed in this way. So it's a surface integral over a sphere at a certain distance r over the pointing vector, the time average pointing vector, so the power density flowing through the sphere in the radial direction. In one of the previous web lectures, we derived an expression for the time average pointing vector, and we were able to rewrite this pointing vector in terms of the field components of the electric field far away from the antenna, so in terms of E theta and E phi. Now, by performing this integration, if we know the far field components of an antenna, then we can calculate the total radiated power, and as a result we can determine the radiation resistance of the antenna. In one of the following web lectures, we're going to determine the electric field far away from the antenna, and we're also going to show how you can calculate the radiated power and the radiation resistance. In this equation we also have the free space impedance, which we already introduced, and that is equal to 377 ohm. Now, once we have obtained the antenna impedance, the complex antenna impedance, we can look at the antenna in terms of the scattering parameters. Let's assume we have an incident amplitude of an incident TEM wave, for example from a transmission line which is connected to the antenna. Because of the antenna impedance, part of this input wave will be reflected back towards the transmission line or electronics, indicated by B. The relation between A and B is of course the reflection coefficient, the input reflection coefficient, and can be rewritten in terms of the impedance of the antenna, ZA, and the impedance of the connecting transmission line. And in this case we have used the superscript T in order to indicate that this is not related to the free space impedance, but this is related to the characteristic impedance of the connecting transmission line. In summary, in this web lecture we introduced a circuit model for the antenna, and we have shown that the radiation resistance can be calculated once you have determined the total radiated power of the antenna. And we've also shown that you can determine the input reflection coefficient when the antenna is connected to a transmission line. Thanks for watching and hope to see you next time. Welcome. In this lecture we're going to talk about phased arrays, and here is an example of a phased array. This particular prototype was developed in my group in the past years, and this is a prototype for future millimeter wave 5G wireless communication. So it will be used as a base station for 5G communication. Now today we're going to talk about phased arrays, and in particular I would like to introduce the concept using linear arrays. And up to now we didn't talk about antenna theory in order to be able to calculate the electric and magnetic field far away from the antenna. That will be done in the upcoming lectures, but the knowledge we have now already is enough to analyze linear arrays of isotropic elements. So the objective of this lecture will be first to introduce the concept of phased arrays. We're going to derive an expression for the radiation pattern of linear arrays using isotropic elements, and we're going to introduce the array factor. Now, applications of phased arrays, traditionally phased arrays are used in more professional applications, like for example in radar, but also in radar astronomy. And this photo shows an example of a prototype which was built about 20 years ago for the Square Kilometre Array, which is a new instrument which is currently being built in Australia, South Africa, to observe the universe, the early universe. And this particular prototype was only 1 square meter of such a large array. And you will recognize multiple elements. In this case, bow tie elements were used. Another example is of course the 5G base station for millimeter wave 5G. The main feature of phased arrays is that it can provide a focused beam which can be scanned electronically, so without the necessity to move mechanically the antenna. And that's a very interesting feature. Now, let us look into the functionality of phased arrays, and we will do that by analyzing a linear array of isotropic elements. And in this linear array we have k antenna elements, and each antenna element is spaced by a distance dx. So all the elements have the same spacing with respect to each other. Now the signals which are received by the antenna elements are input for electronic circuits. And these electronic circuits, they manipulate the amplitude and the phase of the received signal from each of the antenna elements. And finally, after this amplitude and phase manipulation by the electronics, we sum all the signals, and that results in the final signal S, received by this linear array. Now, in case of an incident wave, which is represented here by a wavefront, from a certain angle, with respect to the z-axis, in this case theta, we see that the wavefront hits element k first. And the wavefront will hit element k minus 1 in this particular example secondly. And the time delay between the received signals from element k and k minus 1 is indicated by dx sine theta. So that's the distance that you observe here in this figure. So let's consider a linear array of isotropic antennas, and let us have a closer look at the received signal by element k. And this signal can be written in this form, where you recognize the k naught, which is the wave number in free space. It's 2 pi over lambda naught, where lambda naught is the wave length in free space. And the phase term is shown here. And the phase term you can check by substituting k is large K minus 1. And then you find that indeed the phase difference between element k and k minus 1 pops up. Now, it's very convenient for further mathematical manipulations to change the phase reference to element k is 1. And by doing that, we get a modified signal sk, which is given by this expression. And what we did is, in fact, we subtracted the phase of element 1, which is shown here. Now, next step is that these received signals by the individual elements are manipulated in the electronics. And the electronics manipulate the amplitude and the phase. And the amplitude manipulation can be done, for example, with a variable gain amplifier. And modifying the phase is done in a phase shifter or in a time delay unit. And after the manipulation, we sum all the signals in a coherent way. And then we arrive at the so-called array factor, S, which is a function of theta, the direction of the incident wave. So it's a summation over the complex weights added by the electronics and the signal Sk. By substituting the expression we found for Sk, we arrive at this expression, and we can further simplify that to this form, where we have used the particular choice that the phase added by the electronics, phi k, is k naught times k minus 1 dx sine theta naught. And theta naught is the scan angle. So that's the angle where the array is most sensitive for the incident wave. Now let us take a closer look at a linear array by considering an example. And we're going to look at the radiation pattern that we already introduced in one of the previous web lectures. But the radiation pattern can be obtained by considering the power levels received by the linear array. And of course, then we have to square the received signal S. We normalize it to the maximum, and the maximum occurs at the scan angle theta naught. Now, radiation pattern is always plotted in dB scale, so we have to take the log 10 of this function f and multiply it with 10, because we're talking about powers. Now, the example we're going to look at is an example with 16 elements with a spacing of lambda over 2, so half wavelength. And we're going to consider a uniform amplitude weighting of the electronics. And we're going to consider two cases. The first one is broadside scan, so theta naught is 0. And the second case is scanning towards an angle of 40 degrees. The radiation patterns that you find then, first for the broadside case, are shown here. So we observe a first side lobe. We have a main beam, and next to that we have a side lobe. And the first side lobe appears at about minus 13 dB. And that is due to the fact that we have chosen for a uniform taper. Now, the 40 degree scan case, you indeed observe that the main beam has moved to 40 degrees, and the side lobe levels have the same kind of peak level as shown for the broadside scan, so also at minus 13.2 dB. Now, there's also a very interesting relation of the array factor with a discrete Fourier transformation, or even a fast Fourier transformation. And that can be very useful when you implement such a code in, for example, in MATLAB, to make it more computational efficient, especially when we talk about very large arrays. Now, the array factor we already derived, and if we introduce the coordinate u, where u is equal to sine theta, and u naught, which indicates the scan angle, is sine theta naught, we see something very interesting, because if we write down the equation for a discrete Fourier transformation, which is shown here, you see already the similarity between both summations. And by comparing the phase in these exponential terms, we can observe that if we take this particular choice, that u minus u naught is equal to lambda naught times n minus 1 divided by k dx, then the DFT is exactly the same as the array factor. So that can be very useful and is of course used in a lot of codes which are already existing. Now, in the particular case that k is a power of 2, so the number of elements is a power of 2, then of course the DFT is an FFT, and which is even more efficient from a computational point of view. So as a summary, we have introduced phased arrays as a first nice example of an array system without going into the more advanced antenna theory. And we considered a linear array. We derived the array factor. We've shown the relation with the discrete Fourier transformation. Well, note that we only considered, of course, isotropic elements. And in the next web lectures, we're going to introduce vector-based antenna theory. And by doing that, we can extend the theory that we introduced today to real antennas. For example, microstrip antennas or waveguide antennas or whatever. Hope to see you back in the next web lecture. Welcome. In this web lecture, we're going to continue looking into radiated fields, and today we're going to look into the far field. So, in the previous web lecture, we derived the general expressions for the electric and magnetic field due to an antenna, current source on an antenna, and those expressions were valid both near the antenna but also far away from the antenna. And since antennas are intended to radiate, so we are more interested in the far field properties, and that's what we're going to investigate today. So the objectives of this lecture are first to introduce the far field approximations. We're going to derive the far field condition, so when are we in the far field? Based on that, we're going to derive the general expressions for the electromagnetic fields in the far field of the antenna, and at the end we're going to look into the radiation pattern. Now, let's start with the configuration at hand. So it's the same one as we discussed last week. So we have a kind of general volume V naught where the antenna is located in. We have currents there. And outside the antenna we have an observation point P, indicated by the position vector R. And we would like to know the fields at this observation point. Now, we derived the general expression. First for the vector potential, which could be written in this form as an integration over the current distribution and the Green's function. Related to the vector potential is the magnetic field, which can be found in this way, and the electric field was found by this equation. Now, let's first start with the first two equations and see if we can introduce approximations and simplify it. Now, substituting the second equation in the first one gives us the relation between the magnetic field and the current distribution on the antenna. And we introduced here phi, which is a function just to simplify the notation. And it's related to the Green's function, as you might have observed. Now, this phi function is a function of r, the observation point, but also a function of r naught, which is the position vector for indicating the source points, so where the currents are. The nabla operator, I added the r here as a subscript to be sure that we don't forget that the nabla operator only works on the position vector r, so on the observation point. And that feature we can use to further work out this relation here. The integration is done over r naught, so over the volume v naught. So keep that in mind. Now, the first step in rewriting the whole expression and introduce approximation is to rewrite this integrand that we are using in the integration. Okay, so let's take a closer look at this expression. Nabla times the current distribution times the function phi, and wrote down the function phi here, which is related to the Green's function. The first step that we can take is to apply the product rule. And this gives us then the following expression. So we can say, okay, first we do the derivation towards the current distribution. So we get this. Function of r naught plus the second derivative is then first the derivative to the function phi times the outer product with this vector. You can check for these rules. You can also check the appendix in the book, of course. Now, the interesting observation is that, and that's why I used this special subscript here, r, is that the derivative is towards r, and this function, the current distribution, only depends on r naught. So that means, if we take another color, that this is equal to 0, and that simplifies, of course, our expression. Now, so we only have to consider the second expression. The first step we can do here as well to work out this del nabla of this phi function is to apply the product rule again. So doing that, we observe two functions. Of course, we have 1 over 4 pi. And then we have the first one is 1 over r minus r naught times the exponential plus 1 over 4 pi times this 1 over r minus r naught, and then over the exponential. Yeah, so that's again the product rule. Okay, the first term here, that's a nice exercise for you. This first term. If you do the derivatives, you will find that you get this relative simple solution, r minus r naught absolute value. And the second term, the second derivative, I should say, that we need to work out, this one, over the exponential. That appears to be equal to minus jk naught r minus r naught. And then again this term divided by r minus r naught absolute value. Yeah. So substituting these two expressions into the equation above, we can then say, okay, then we arrive at this expression. Is then first one minus 1 over 4 pi r minus r naught divided by r minus r naught absolute value times the exponential and then we have two terms, so we have 1 over r minus r naught squared, which comes from this part here, plus j, that's this part, k naught r minus r naught. Yeah, and we can simplify that by introducing a new parameter, rd. One over rd squared plus j k naught over rd, and rd, the vector, is r minus r naught. This term here, this is the unit vector in the rd direction, and well, that means that this term here, where we were looking for r naught times v, is apparently equal to minus 1 over 4 pi jk naught, yeah, plus 1 over rd times the exponential k naught rd divided by rd times the unit vector in the rd direction, outer product with the current distribution. Okay, so let's see where we are now. So we started with this expression for the H field, where we worked out the integrand in more detail, and we found this expression, which is still without any approximation. We used the notation of Rd, which is the absolute value of the difference vector between R and R naught. And if we combine these two expressions, we can write the H field in terms of this integral, which still looks quite hard to solve in an analytical way for, let's say, a given current distribution. Now, let's see if we can introduce approximations, because we assumed that we were in the far field. Now, if we look into this configuration again, so we have an observation point P, and let's assume that this point P is far away from the antenna. So that means that R is much larger than R naught. And if we look at the integrand in this integral, then we see a couple of RDs popping up, and let's go through all these particular expressions. So the first term is this one, so j k naught plus 1 over rd, and if r is much larger than r naught, then you can approximate it by j times k naught. The second rd pops up here. So if, again, R is very large, then RD will be approximately equal to R. In the unit vector in the direction of RD, we can hold the same kind of storyline where if R is much larger than R naught, then the unit vector will be approximately similar to the unit vector in the R direction. That leaves us with this expression, which already looks much more clean. The only term we didn't approximate yet is the term in the exponential. And there it's more difficult because there you could also say, well, RD is almost equal to R, but that's not good enough because this is a periodic function. And we have to look into it in a little bit more detail. So we have to work out this expression for the H field in more detail. And this is already a cleaned up version, but we still need to work out the exponential term here. And we need to find an approximation for RD. And RD was the difference between R, the position vector in the far field, and the position vector indicating the source point. And we assume that R is much larger than R naught. Yeah. So that's our assumption. Now, let's have a closer look at RD. So RD can be written as a square root x minus x naught squared plus y minus y naught squared plus z minus z naught squared, the square root. And we can rewrite that, well, it's in this form where we have x squared plus y squared plus z squared. So this is already r squared. Minus 2 times x naught plus y naught plus z naught plus this term, which is equal to r squared. Yeah. I'm reshuffling it a little bit, bringing r in front. So this is r. This is r squared, and then the square root is r. We have 1 minus 2 times this term. Divided by r squared, because we put the r in front, plus r naught squared divided by r squared. Now, we have this assumption here, and that means that we can use the Taylor approximation, and as you know, the approximation of square root 1 plus x is approximately equal to 1 plus half x minus 1/8 x squared, and higher order terms. Of course, we're going to neglect them at the end. Well, x in this case is then this function here. And if we use that, we find that RD can then be written as R times 1 plus a half times this. So this was minus 2r squared x naught plus y naught plus z naught. Yeah, plus r naught squared divided by r squared. Yeah, plus, well, minus higher order terms, and we're going to forget about them, is equal to r 1 minus x naught plus y naught plus z naught divided by r squared plus r naught squared divided by 2 r squared minus the higher order terms. Yeah? Well, we can approximate this if we neglect the higher order terms. So we see that this is equal to r minus
And this can be written as R vector divided by R inner product with R naught. Yeah, check that yourself. And this is, of course, the unit vector here, so this can also be written as R minus inner product of the unit vector in the R direction with R naught. And this approximation holds when this term here is small enough, and that means that this term, don't forget about this R, we have R naught squared divided by 2R should be small enough. And in the past, people and antenna community decided that small enough means lambda naught over 16. So it should be smaller than lambda naught over 16. And what does it mean? If you want to know what it means, you have to look into this argument here. So that means that we have to look at k naught times lambda naught over 16, and that is 2 pi over lambda naught times lambda naught over 16 is pi over 8, and that is 22.5 degrees. So that means that, worst case, we make an error of 22.5 degrees in this phase term here. Now, if we have a practical antenna somewhere positioned in our coordinate system, x, y, z, like this, with the largest dimension d, so it could be a reflector antenna or something, then R naught max is d over 2. And if we apply this criterion, then it means that d over 2 squared divided by 2r should be smaller than lambda naught over 16. And that brings us to the well-known far field criterion, which we already introduced in one of the previous web lectures as well, that r needs to be larger than 2d squared over lambda naught. So this is the far field criterion. So keep in mind that this is related to this maximum error of 22.5 degrees. Okay, so we have now derived this expression for the magnetic field, and we use the approximations for RD, and we have derived also the far field condition. So let's have a closer look at this expression now. So we first observe the spherical expansion of this wave, so the 1 over r and this phase relation, the exponential phase relation. The second observation is that indeed, since we have time harmonic signals and fields, the wave propagates in the plus r direction, so away from the antenna, as you expect. This term here in the exponential is in fact the phase difference between the source point r naught and the origin of the coordinate system. And we can observe that the H field has no radial component, which means that the H field can also be written in this form. So in terms of two components, H theta in the theta direction and a component in the phi direction. Now, the next step, step 3, is to look into the electric field. So we have done the approximations for the magnetic field. We can do this similar kind of approach for the electric field, starting with this equation. If we do that, we arrive at the same kind of approximation with the same far field condition as given here. And we arrive at this expression shown here, which looks very similar to the magnetic field, but has a few extra manipulations and constants. Again, the electric field has no radial component, similar to the magnetic field, and therefore we can write the electric field in terms of these two components in the theta and the phi direction. So to summarize the approximation, we have the electric and magnetic field given here, and if we look a little bit more closely, then we see that the electric field has, apart from some extra constants, has an extra outer product, UR times this integral, as compared to the H field. And that means that the electric field is perpendicular to the magnetic field, like this. And that's what we are looking for, because we already said before that in the far field, the electromagnetic field behaves like a TEM wave, a plane wave. And that's indeed what's happening. If we combine both expressions, we see that we can write the H field in terms of the electric field in this way, where we observe the expression for a TEM wave, and the 1 over Z naught, the Z naught is the characteristic impedance of free space, which is 120 pi, which is approximately 377 ohm. So, with that, we can go to the next step and look into the radiation characteristics of an antenna. And the first thing to do there is always to calculate the time average pointing vector, which was given by this expression. We introduced that before. So we can now substitute the relation between the E and the H field, shown here. If we combine those two equations, we can express the time average pointing vector in this way. And we can observe that indeed the power flow is in the R direction. And that's what you want for an antenna. And the pointing vector is expressed in terms of watt per square meter. So it's really the directional power density. Now, with the pointing vector, we can determine the radiation pattern of the antenna. And this was already introduced in one of the previous lectures. And can be calculated in this way, where we normalize the power density by the maximum value. And that, of course, depends on the antenna at hand. The radiated power per element of solid angle is shown here as well. Now, having said that, to summarize today's web lecture, we have looked into the expressions for the electric and magnetic fields, and we have derived the far field expressions for those fields. And this formulation that we introduced here holds for any antenna. From this, we can determine the radiation characteristics, like the pattern, but also the directivity, gain, and also the radiation resistance. And in the next web lectures, we will show how you can use these expressions for all kinds of antennas, like wire antennas, but also aperture antennas. Hope to see you back next time. Welcome. Today we're going to talk about wire antennas, and an example of a wire antenna is, of course, an antenna which is put on top of such a digital radio or FM radio receiver. And the wire antenna in this case is an antenna that can be changed, can be tuned in length, and this is a monopole antenna. And today we're going to talk about these type of antennas. So our lecture is about wire antennas. The objective of this lecture today is to first apply the general formulation to analyze these type of antennas. And we will consider dipoles of various lengths. We will consider the monopole, as in the example of the digital radio receiver. And we will talk about folded dipoles. We will show that a wire antenna has a much higher radiation resistance as compared to the electric dipole, and that makes the wire antenna much more convenient to use. Now, let us take a closer look at the configuration at hand. So we have a dipole consisting of two arms, so two metal wires. Each arm has a length L, so the total length of the dipole is 2L. And the dipole is connected to a generator, a transmitter, could also be, of course, a receiver in the receive case, but let's consider the transmit case. So we have a generator that generates power, and that power is transformed through a transmission line towards the dipole, and at the feed point of the dipole it generates a voltage. And the voltage will again create a current along the dipole as indicated here. Now the current along the dipole can be represented mathematically by this expression, where we recognize a few things. So first we see that the current will be oriented along the z-axis, so the vertical axis in this case, because the dipole is oriented along the vertical axis. Next to that, we will assume that the wires are very thin as compared to the wavelength, which is in the practical situation always the case. So mathematically we can represent them by delta functions, as we did also with the electric dipole, but now of course only in the x and the y direction. The z variation of the current can be represented by a sine function, and this sine function represents the current along the dipole quite correctly, especially close to resonances. If you want to have a more accurate description also at other frequencies, so not at resonance of the dipole, it's better to use numerical techniques like the method of moments. And we're going to talk about that in one of the upcoming lectures. But for now we will assume we have this sinusoidal current distribution along the dipole. Now we can visualize that as well. So I've plotted here 5 dipoles, each with a different length. So the first dipole in this diagram has a length of half wavelength. And you can see that the current indeed is represented by half a sine function. So the maximum occurs in the middle, at the center, and the minima, so the current is 0 at the tips of the dipole. And that makes sense because, you know, the electrons cannot escape from the metal. And we assumed that the dipoles, by the way, the wires, are ideal, perfect conductors. Now, if we look, for example, at a dipole with the length of lambda, so twice the length of a half wavelength dipole, you see indeed that we now have 2 maxima, and also in the middle we have a minimum in the current. And well, if you go to longer dipoles, then of course you will have more harmonics of the current along the dipole, as shown in this diagram. Now, how can we calculate the radiation characteristics? Now, we just apply our recipe that we introduced. So our recipe for the far field is given by this expression. So this is the electric field, where we recognize some constants. We recognize the spherical expansion again, and we have to do some outer products. And we have to perform an integration over the source. In this case, the source is the dipole antenna and the current along the dipole antenna in particular. Now, this current distribution on the dipole is represented by the function that we already introduced. So we can substitute that in the integration. The vector product that we need to work out is relatively simple. So it's in this case u theta sine theta. So it means that the electric field will only have a component in the theta component, in the theta direction, I should say. For these outer products, the vector products, please check again the appendix of the book and you can find all the details. Now, combining these 3 expressions and using the fact that if we have the delta function in the integral, as we did with the electric dipole, we can make use of the special properties of the delta function. At the end, we have this expression for the electric field, so we have only a component in the theta direction, and this component in the theta direction still has an integral over, of course, the sine function and over the dipole. So we have to integrate from minus L to plus L in the z direction. This integral, let's call it I over z naught, can be done in an analytic way. I'm going to show that in the next slide, step by step. So this is the integral that we need to work out. the first thing we're going to do is we're going to write out Z0, so for the domain -L to 0 and for the domain 0 to L. So we split it in two integrals as shown here. And we can make use of the fact that we can substitute in the second integral, we can substitute a new variable, let's say Z0 tilde is equal to minus Z0. If we do that, then the boundaries of the integral will swap. And we can write the second integral also in terms of an integral from 0 to L. In this way we can combine both integrals, and we observe, if we do that, that we have two exponentials, one with a positive argument and one with a negative argument. And of course, if we combine them in one integral, then we get a cosine of the argument. And that's shown here with a factor 2 in front. So this integral is easy to solve because we can use the property, the general property that 2 times sine alpha times cosine beta can be written as the sine of the alpha minus beta plus the sine of alpha plus beta. So we can split it in two integrals again, and that's just a simple integral over a sine function. If we do the math, then we at the end obtain this relation as shown here. And we observe indeed that this integral is only dependent on theta and of course on L and K0, where the wavelength is included. So this brings us again back to the expression for the electric field. So if we substitute the expression for the integral that we have analyzed into the expression for the electric field, we get this relation, which results in finally in this equation here, where we again recognize the spherical wave expansion, and we recognize a function that depends on theta only. Having E theta, we have the electric field. We can calculate, of course, also the magnetic field because there's a TEM relation between the E and H field. And as a next step, we can calculate the power flow, so the pointing vector, the radiated power. And that was given by this expression as we used before. We know the electric field, so we can easily calculate the pointing vector as well. And again, we observe that the pointing vector is directed in the radial direction, indicated by the unit vector UR. Now, with the pointing vector, we can calculate the radiation pattern. So we normalize the total or the radiated power by its maximum, and we can substitute the expression for the pointing vector. And now let's take a few examples to plot this function f. And first consider a dipole with a length of a half wavelength, which is the most commonly used dipole in applications. Let's consider a polar representation of this radiation pattern, as we also used for the electric dipole. Doing that, we get this plot. And the dipole, the half wavelength dipole, is positioned in the middle, as indicated by the blue arrow in this diagram. So it's vertically directed, and you can see that the radiation maximum occurs at an angle of theta is 90 degrees. The full line here is the half wavelength dipole, and it has a half power beam width of 78 degrees. And you might remember that the electric dipole, which is plotted here by the dotted line, had a half power beam width slightly higher, but it was 90 degrees. So the half wavelength dipole is a little bit more directive than the electric dipole, but it's not so much different, I would say. The main difference we will talk about in a minute. Now, if we further increase the length of the dipole, so for example to a length of lambda, so twice the length of a half wavelength dipole,
and again plotted in a polar diagram, we get this result. So you see that the main beam of the lambda not wavelength, one wavelength dipole is much more directive, so it's much narrower. The half power beam width is about 47 degrees. And if you compare that to the electric dipole, then indeed you see it's much more directive, which could be useful in applications where you want to have more directive beam. If you further increase the length of the dipole, so for example to 1.5 times the wavelength, and again plotted in a polar diagram, we observe something interesting. We get multiple maxima for the dipole. And you might remember from a few slides before that we plotted the current distribution along the dipole, and if the dipole length is much larger than half a wavelength, you had multiple maxima of the current, so multiple harmonics, and that results also in multiple harmonics in the spatial domain, so in the radiation pattern, as you can see. So for comparison, the electric dipole is shown again. So this type of very long dipole is not very useful because, at least not in most applications, because their multiple maxima is usually not very beneficial. Now, apart from the radiation pattern, we can look into other radiation properties, as we also did with the electric dipole. So first, of course, we have to calculate the total radiated power, and we can do that by integrating the Poynting vector over a sphere with radius r. Substituting the expression for the Poynting vector and looking into the integral that remains over theta and phi, well, we see that the integrand does not depend on phi, so the integration over phi is easy. What remains is an integration over theta. So if we work out the integration over phi, gives us 2 pi. The integral over theta can be done in closed form for a half wavelength dipole, for example. And the result is that this integral for half wavelength dipole is equal to 1.218. And if we substitute that, we find that the total radiated power is equal to half times 73.1, and that's a very important number, times the absolute current squared. Yeah? So you already recognize here the expression for the total average power when you would have a circuit with a resistance of 73.1 ohm. Well, I will come back to that in a second. So this holds only for a half wavelength dipole, but you can do the integral also for other lengths, of course. So the radiation properties for a half wavelength dipole, so let's continue with that. Let's first look at the directivity and the antenna gain. It was defined, the directivity, as the maximum of the radiated power density by this particular antenna divided by the power density that would be radiated by an isotropic antenna, where you put a total power PT in. Now, we calculate the total power. So in this way, we can calculate the directivity. It occurs at an angle of 90 degrees, and it's equal to 1.64 for the half wavelength dipole. If we assume, and we do that for now, that we have perfect conductors, so there will not be any ohmic losses in the antenna gain is equal to the directivity, so also 1.64, and in dBIs it's equal to 2.15, which is slightly higher than the electric dipole, and that's also expected because the directivity of the dipole, so the beam width, was also somewhat narrower than the electric dipole. The input impedance, very important, because that was the weak point of the electric dipole, as you can remember, where the radiation resistance was really low, like much smaller than 1 ohm, so not very practical. In this case, you might already have recognized it. The radiation resistance, Ra, will be much more realistic. We already calculated the total radiated power, and if we divide it by half times the current squared, then of course we get the radiation resistance, and that was 73.1 ohms. And that's a very nice number because it's easy to match to a transmission line in practice. Now there are also other types of wire antennas. I already showed the digital radio receiver with this monopole type antenna, which is also represented here in this diagram. So in a monopole antenna, one of the dipole legs, as to say, is replaced by a ground plane. So in the middle of the dipole, a ground plane is placed, and the lower leg is not used anymore. The length of the monopole is therefore a quarter wavelength, and along this monopole we have a current, and the current is introduced by a feed line, which is now in this case an unbalanced feed line. So it's a kind of strip or wire above a ground plane where you have a TEM wave propagating towards the antenna and exciting the monopole antenna. Monopole antennas can also be fed, for example, very easily by a coaxial cable. So then the inner conductor is extended to a half wavelength monopole, and the outer conductor is connected to the ground plane, for example. Now the ground plane can be seen in practice as what is known as the image concept. So we can use the image concept to show that the radiation properties of a monopole are in fact identical to the half wavelength dipole, except that we only radiate energy in the upper half space and not below the ground plane, of course. That means that if we integrate the fields over a sphere, we only integrate over a half sphere, and that also means that the total radiated power will be half of the total radiated power of a half wavelength dipole, and that's indicated here. So substituting that in the expressions for the directivity first and for the radiation resistance, we find that the directivity is twice as high, so 3.28. So that's in dBs, it's 5.15 dBi. And the radiation resistance will be half of the 73.1 ohm radiation resistance. But still, this is a very practical value, easily to match to a transmission line or to a transmitter or a receiver. Now, another type of wire antenna is the folded dipole. It's also quite popular. It's shown here. So it's again half wavelength, but now oriented in this case along the horizontal axis, but of course you can also use it along a vertical axis. But the folded dipole is fed by a twin wire transmission line, again like also the normal dipole, but it has the nice property that the radiation resistance is 4 times higher approximately as compared to the standard dipole. So we have a radiation resistance of approximately 300 ohm, which makes it easy to use in certain applications where you have a feed line with a somewhat higher impedance. For that reason, these type of folded dipoles, because they also have a radiation pattern which is quite similar to a normal half wavelength dipole, which is already quite similar to an electric dipole, so very broad. They are very popular in use in phased arrays, for example. And this photo shows a quite big, a large phased array with 1024 elements, and in this case the folded dipoles are used in this phased array. Now, to summarize, we have calculated the radiation properties of wire antennas using our recipe. We have shown that the half wavelength dipole has a radiation resistance of 73 ohms, which is much more useful than the electric dipole. We also introduced the monopole antenna and the folded dipole. And I hope to see you back next time. Welcome at today's web lecture. Today we're going to talk about horn antennas, which is a type of aperture antenna. Well, this is an example of a horn antenna. This is a conventional classical horn antenna with an aperture here. And at the back side you see it might be connected to a rectangular waveguide. Well, these are traditional horn antennas. There are also more modern horn antennas, systems used in systems like phased arrays. And this is an example of an open-ended waveguide, which is in fact a waveguide which at the end is open-ended. So you can also say it's a horn antenna. And these antennas are connected, as you can see, to what's called a transmit-receive module, where the electronics for transmitting and receiving the signals is being done. Now, let's look at today's lecture, the horn antennas. The objective of this particular lecture is to apply the equivalence concept that we introduced last time and to apply our new far-field recipe to horn antennas. Using that concept, we're going to calculate the radiation properties of a uniform rectangular aperture, which is a kind of first-order model for a horn antenna. Now, let's first look at the model. So I already shown you an example, which is in this case a classical rectangular horn antenna. It's square in this case, but it can have, of course, a rectangular shape, like shown here, where the length of the horn is given by A and the height is given by B. So A is along the x-axis and B along the y-axis. Now, we will assume in this model that the electric field is oriented along the y-axis in the aperture of the horn, as indicated here by the green arrows. So we assume a uniform electric field in this aperture, in the direction of the y-axis. Now we can apply our equivalence concept and our recipe. So this was introduced last time. So we have an original problem where we have currents being both electric or equivalent magnetic currents within a volume, within the antenna volume. And we could define an equivalent problem where we only have to consider the tangential field components along the closed surface S0, as indicated here in the right picture. Once we found that, we can determine the far fields using the recipe that we derived last week, where we first have to define a proper closed surface S0, and we have to find the tangential field components on this closed surface. So the first step is then to select a proper closed surface. And in this case, we're going to split it in two surfaces, the aperture surface SA and the rest of the horn construction SC. And this is visualized in this cross-section, where you recognize the horn with the radiating aperture and surface SA, and the rest of the horn, including the waveguide connected to it and the generator connected to it, is enclosed by the surface SC, and in total they make up the total surface S0. So the coordinate system is shown here again, and on SC, so that's the first surface, so that's excluding the radiating aperture, we will assume that that's a perfect electric conductor, which means that the tangential electric field will be zero, and we will also assume that currents that might flow on this surface can be neglected. So also the tangential H field is zero, as indicated here. On the radiating aperture, so on SA, we will assume that we have a uniform electric field distribution directed along the y-axis, and the corresponding H field is given here and is directed along the x-axis. Now, we have now defined the closed surface. We know the tangential fields on the surface, so we can apply our recipe. The tangential ingredients that we have to substitute in our recipe is shown here. So it's easily calculated because the normal vector on SA is equal to the normal vector in the Z direction, and the outer product is then easily found as shown here for both the tangential electric and magnetic fields. So we know now the tangential components. We can substitute that in this recipe that we derived. So if we do that, so the electric tangential field and magnetic tangential field, we arrive at this expression where we need to integrate over the surface SA. So from minus A over 2 to plus A over 2 and minus B over 2 to B over 2. And this integration is not so difficult to do, and we will show that in a second. It is convenient to split the integral over two integrals, LM and LE, and we're going to work out both integrals in more detail. Okay, so let's have a closer look at the expression for the far field, which consists of this spherical expansion of the wave times these two integrals that we need to work out. And these integrals were given by, the first one LM was given by E naught times the integral over the aperture so where we assumed that the horn antenna, the aperture, is centered around the origin of the coordinate system, by the way. The vector product UR times UX, and then this exponential inner product with R naught, and then integration over X naught and Y naught, and the other integral LE was rather similar. So minus E naught times the same integration area over the aperture. And then we have a triple product, UR outer product UY, and then the same exponential integrated over X naught and Y naught. Now, we're going to look in a little bit more detail into solving this integral, and then the LE you can do yourself at home as an exercise. So we have to first consider two vector products. So this is outer and inner product. So the first one, UR outer product with UX. So since we want to express the far field in theta and phi components, it's most convenient to express UX in spherical coordinates. So this is UR outer product with UX written in spherical coordinates. So that's U theta cosine phi minus U phi sine phi. So check the appendix of the book for these expressions. And then you can work out these outer products. So UR outer product with U theta as U phi. So we have U phi cosine theta cosine phi. And then outer product UR with U phi is minus U theta. So with the minus sign we have here a plus U theta sine phi. So that's the first one. And the inner product here, so UR inner product with R naught. So here it's more convenient to express it in terms of Cartesian coordinates because the integration is done over X and Y.
So then we express UR in terms of Cartesian coordinates, and that is like this. So sine theta cosine phi plus uy sine theta sine phi plus uz cosine theta. Yeah, in a product with R0, and R0 is of course in Cartesian coordinates given by this expression. Yeah, so that's fairly easy to work out. So this disappears. So we get x0 sine theta cosine phi plus y0 sine theta sine phi, and that can be written in a more compact form, x0 u plus y0 v. And u and v are given here, and u and v are commonly used in antenna theory, and we will more often use it. Now, so we can substitute this in Lm, so which means that Lm is then the integral. We have E0, and then we have this vector product that we found there. So that's u phi cosine theta cosine phi plus u theta times sine phi. And then we have the integral with the exponential. So, and that's simply the exponential over x0 u plus y0 v dx0 dy0. Yeah. So this integral can be written as a product of two integrals, so over x0 and y0. So let's look at one of them. So for example, the integral over x0. So that's this integral. Well, this is quite common, and the result is this x0 u in the boundaries minus plus a over 2, and that at the end gives us this expression, two exponentials, so a over 2 minus the same one, but then with a minus sign. Sorry, so this is u, sorry for that, times a over 2. And this is of course equal to 2j times sine of this argument. And that brings us to this result. So we have a sine over this argument. So k naught a u over 2 divided by k naught u a over 2. And this is equal to a times a sinc function. Now the other integral over y we can do in a similar way. We also get the sinc function, but then b times the sinc function, and the argument is then bv. Combining that, all these ingredients, so let's work out further here. So then Lm is given by a times b times e naught times this vector expression. So that's u phi cosine theta cosine phi plus u theta sine phi times the two sinc functions. So sinc k naught a u divided by 2 times sinc k naught b v divided by 2. And well, if we work out LE in a similar way, we can substitute that in the expression above, and then we find the electric field in the far field region.
So in this way we can derive the far field expression for a uniform aperture by substituting the solutions for both integrals Lm and Le, and we arrive at this expression where you can see both sinc functions expressed in terms of the u and v coordinates, which are related to theta and phi. And we recognize two components, one in the theta direction, e theta, which by the way is 0 in the phi 0 plane, as you can see by substituting phi 0 in sine phi, and that's called the H plane. So it's the plane where the H field is directed towards. In the phi is pi over 2 plane, so in the 90-degree plane, which is called the E plane, we recognize that E phi is 0. From this we can construct the radiation pattern, which is the normalized radiated power, as shown here, and the maximum occurs for theta and phi is 0. And this way we can calculate the radiation pattern. So look at some properties of these horn antennas with uniform aperture. So the radiation pattern is given by this expression, and due to the properties of the sinc function, we find that if we increase A, we obtain a smaller beam in the horizontal plane, so in the XZ plane. In a similar way, if we increase the height B, we get a smaller beam in the vertical plane, so in the YZ plane. And also due to the properties of the sinc function, the first side lobe will occur at minus 13.2 dB. So that's a strict result of the choice of our model to have a uniform aperture. So let's look at an example of an horn antenna modeled as a uniform aperture. So in this example we have an aperture with a size A 4 lambda and B 2 lambda, and the three-dimensional radiation pattern is plotted here in terms of U and V coordinates. The directivity of this particular horn antenna is 20 dBi. Now if we take a cross-section of this pattern, which is more convenient to use often, so for example in one of the principal planes, so in the V is 0 plane, so phi is 0, then we get this radiation pattern, so as plotted here in terms of the horizontal axis is theta, and the vertical axis you find the normalized radiated power in dBs. Some properties, so the half power beam width, so that are the 3 dB points on the main beam, is in this case 12.4 degrees, and the first side lobe indeed occurs at minus 13.26 dB in this case. So to summarize, we have shown that horn antennas can be modeled as a uniform aperture. By using the tangential fields in the aperture, we can use our recipe to calculate the radiation properties. We saw that for the uniform aperture we get the first side lobe at minus 13.2 dB. And of course, if you want to know the radiation properties of a real horn antenna with a more realistic aperture distribution of the fields, you should use an EM solver to find this particular field distribution in the aperture. But you can still use the same recipe at the end of the day to calculate the far field patterns. Thank you for watching and hope to see you next time. Welcome again. In this lecture we're going to talk about reflector antennas. You know, these large antennas that you might recognize from TV reception, for example. So the objective of this lecture is to again apply the equivalence concept and our far field recipe
to analyze reflector antennas. And of course, we're going to determine the radiation properties, and we're going to assume that the apertures, which is a model of the reflector antenna, is a circular aperture. And at the end, we're also going to introduce what's called tapering to realize more well-defined low side lobe levels in the radiation pattern. Now, let's first have a closer look at reflector antennas, at the applications of reflector antennas. And one of the well-known applications, of course, is the use of large reflector antennas, also known as dishes, in radio telescopes. So what you see here in this picture is a photo of the Westerbork radio telescope, consisting of 16 reflector antennas, and each reflector antenna has a diameter of 25 meters. And this is used to observe the universe. Another application well known for reflector antennas is radar, for example, for air traffic control, but also for military applications. And of course, the satellite dish antenna is also very common in most countries. So probably you're all very familiar with reflector antennas. Now, how to analyze them? Let's first look at the model that we're going to use. So we're going to assume that we have a parabolic reflector antenna, which is fed in the focal point, so at the distance f from the reflector. And the reflector has a diameter d, as indicated here in the figure. At the focal point, we use a feed antenna, which often is a horn antenna that we discussed in the previous web lecture, but can also be, what's often done nowadays, can also be a phased array feed. And in that way, you create what's called a focal plane array, where you can even scan the main beam generated by the reflector antenna somewhat. But let's go back to this first simple model, where we have this feed antenna. And this feed antenna generates a spherical wave that will propagate towards the reflector. Now, let us take a closer look at this particular point A on the reflector, as indicated here in the figure. And let's assume that we have an aperture surface, as indicated here by SA. And we're going to look into a wave that propagates from the feed point, as indicated here by the arrow, towards A, and then is reflected by the parabolic reflector and will hit the aperture surface SA in the point B, as indicated here. Now, the reflector transforms the phase front generated by the feed antenna, which is a spherical phase front, into a planar phase front at the aperture surface SA. Now, because of that, we can model the reflector antenna as a uniform circular aperture, which is a first order approximation of a real reflector, because we neglect effects that might occur at the edges, for example, by diffraction. Now, this uniform circular aperture looks like this. So we have this circle, which is positioned around the center of coordinate system, as indicated here. And within this aperture surface, we assume that the electric field will be oriented in the vertical direction, in this case in the x direction, and the associated H field will be directed in the y direction, as indicated here by the red arrow. So this is the model that we're going to use in our recipe that we derived in order to calculate the far field. So the recipe we have is based on the equivalence principle, as we already used a couple of times. So we have an original problem, which is the feed and the reflector, etc., with currents. And we're going to replace it by an equivalent model where we only are going to consider the tangential magnetic and the tangential electric fields on the surface enclosing the antenna. And then if we have done that, we could... so let's first look at SC. So this is the coordinate system. So on SC, which is the back of, we will tangential components. So as indicated here, using the normal of the surface SA, which is now directed in the Z direction, we can calculate these tangential field currents, I should say, in this way. And next step is to use that in our integral. So we have these equivalent electric and magnetic currents, as indicated here by the tangential fields. And we're going to substitute that in the integral. So that means that we're going to replace E outer product with the normal by the expression here. So that's minus E naught times uy, so the unit vector in the y direction. And for the tangential component of the magnetic field, we're going to do it in a similar way. Now, finally, we arrive at this expression as shown here, where we have to work out the integration over the aperture surface. So it's an integration where phi runs from 0 to 2 pi, and where the radius runs from the center of the aperture, circular aperture, so that's 0 to the outer circle. So that's indicated by the radius A. And A related to the diameter, because the diameter is 2 times A, of course. So now we have to work out this integral. Okay, so we have to integrate over the aperture. The uniform circular expression for the electric field was given by this expression, so minus j k naught E naught divided by 4 pi r. And then we have this integral over the aperture, phi from 0 to pi and r from 0 to a, so the radius of the reflector. And then we have this unit in the y direction, and we have to work out this outer product, ur times ux. And then we have, again, this exponential phase term that we need to determine as well. Then, of course, we have polar coordinates, so r naught, dr naught, d phi naught. So that's the integral we have to work out. So we have some work to do. So the first one is to look into this outer product. So ur outer product uy. So what we can do is to write the unit vector in the y direction in terms of spherical coordinates, so that we get ur times sine theta sine phi. Although, of course, we don't need it because ur times outer product with ur is, of course, 0. But it's just for completeness. And then we have the unit vector in the theta direction times cosine t, so theta sine phi plus u phi cosine phi. And then this was 0. And then this we can write out in more detail. So ur outer product with u phi gives us, or u theta gives us u phi cosine theta sine phi. And then ur outer product with u phi gives minus u theta times cosine phi. So check the appendix of the book for these plus cosine theta. We have these terms here. 4 pi r, 1 plus cosine theta times this expression, u phi sine phi minus u theta cosine phi. Yeah. And then the integral, again, still to be worked out, of the exponential r sine theta cosine phi minus phi naught, and then r naught d r naught d phi naught. Okay, now the integral over phi, let's look at that. It would not. We find that the electric field can be written by E naught r, and then we have 1 plus cosine theta. We get again this sine phi minus